Okay, so as the organizer, I would like to ask if we are ready to start, because at the beginning of the session, we will play a short intro video, and then I will give the organization to the chair of the session to proceed, if you agree.
For me, we are ready. Yeah. So if you want to start and then hand over to me, it's perfectly fine. Yeah.
The following message is best viewed on an oscilloscope.
So good afternoon, everybody. I hope you can all hear me. I would like to welcome you to this parallel session on accelerators at the ICHEP 2020 conference. So this afternoon, we start with the accelerator session. This is the first block of session 11, and it is devoted to strategies and plans for circular and linear accelerator facilities with potentially high impact on our field. We have 6 presentations scheduled in this session with 15 minutes talk duration. So I ask the speakers to please respect these time limits, and then we have 5 minutes for discussions and questions to each of the presentations. And just a few more words. So the speakers will share their screens and manage their presentations from their own laptop or PCs. And then for afterwards, please push the buttons with hand up so that we can take the questions in the discussion afterwards. Or we will keep the room, of course, going after the end of the session, so we can continue discussing at the end of the 6 talks, if you wish. So I suggest we start directly with the first presentation, which will be by Lucas Malina. And this first presentation will focus on the high luminosity LHC project, and its title is Strategies for Beam Optics Commissioning. So Lucas, please take the screen and go ahead with your presentation.
Can you hear me now?
Yes, we can hear you.
Okay, perfect. So, hello everyone. Thank you, Michael, for a nice introduction. I'm very glad to have the opportunity to talk about beam optics commissioning strategies for high luminosity Large Hadron Collider on behalf of the whole team. I assume that LHC does not need much introduction. It's a 27-kilometer long circular collider built underneath Swiss-French border next to Geneva. It collides mostly protons, but also lead ions in 4 main experiments: ALICE, ATLAS, LHCb, and CMS. And high-lumi LHC will upgrade the LHC. The injector chain is being upgraded as we speak almost. The inner triplets, which are closest to the interaction point, will be replaced, and crab cavities will be installed along with many other new hardware. In the table below, you can see the main parameters important for beam optics commissioning, and that's the beta star, which will reach from 55 centimeters down to 15 for high luminosity LHC.
Sorry, Lucas, to interrupt you, but there is no, you're not sharing the screen. We cannot see your presentation.
You don't see my screen?
No.
Okay.
Can you perhaps try to go out and back in again?
Yeah, I'm trying.
Now it seems to start working. Yes, now it works again. Yes.
Yeah, okay. Okay, where did I stop? Yeah. So in total, high luminosity LHC will increase the integrated luminosity tenfold compared to the LHC, and will happen soon. It will start its operation in 2027. Okay, but now I cannot move slides. Okay, so what is actually the beam optics? In circular accelerators in stable conditions, beam optics is a property of a machine which one can understand as magnets with their powering. There are different types following the magnet multipole expansion. You can see dipoles, which I will not talk about, and then quadrupoles, which do focus the beam and are responsible for linear optics, and higher order magnets, sextupoles, octupoles, which are responsible for nonlinear optics. Magnets are not built perfect. They have errors. They can be a little too strong, little too weak, or be misaligned, rolled, etc. This all changes the beam size or optics. To fix this, we generally adjust the magnetic strength, and we call this optics corrections. Why do we control the beam optics at all? So first of all, to protect the machine from the beam itself, as when the beam is larger and hits something, it can cause severe damage, as you can see in the picture on the right, when lower energy and lower intensity beam of protons hits the copper target, it melts the copper, evaporates it, and splashes all around. In the bottom plot, you can see typical measurement result, sort of so-called beta beating. In red, it's uncorrected, and you see 100% error, while the limit represented by the black lines is about 20%. And we really need to correct the optics to go to the blue corrected. We also need to mitigate the beam instabilities, which may otherwise lead to beam dumps. And when the beams are dumped, there's no collisions, there's no physics, simply machine has stopped. This brings me to the last point, and for some people, the most important one: deliver the luminosity to the experiments. The luminosity is inversely proportional to the beam size at interaction points, and those are related to beta functions, which are the optics properties of the lattice. But in a high luminosity LHC, we may end up in a situation that beams are too intense and more squeezed at the eyepiece. It would cause too large pileup in the experiments. So we need to limit the luminosity in the beginning of the fill. We start with larger beams and squeeze, change the optics if you want, to compensate the decrease in beam intensity from burn-off and just by slowly losing beam. Such technique is called beta star leveling, and the optics is changed simultaneously in ATLAS and CMS experiments. We also need to maintain the luminosity imbalance below 5%. In the plot on the right, you see how the luminosity would look like without any beta star leveling. It would rise too much, so we level it to the blue. And for the reference, you see also in a black and gray the LHC nominal and achieved performance. Every single beta star represents different optical configuration, and all of them need to be commissioned. This is one of the challenges which increases the number of measurements needed. Pushing the beta star lower means that the beta functions at the neighboring quadrupole triplets need to be high. This increases the importance of magnet imperfections, strength, higher order errors, misalignments, rolls, etc. Typically, magnet power supply can also jitter, and this degrades the measurement precision. We need to correct the higher order magnetic errors as they matter because of large beams. This also dramatically increases the number of measurements needed here. But why I'm telling you why this is important? Due to machine protection reasons, we typically measure with a single pilot bunch, which has a fraction of intensity of a nominal bunch. So when we measure, there is no physics, no collisions, so it requires our methods to be time efficient. In total, we need to measure more with better accuracy and as fast as possible. On the longer time scale, the gradual performance increase of high luminosity LHC will sort of give us a time to commission all the optics, as we start on a higher beta star at 30 centimeters and over years squeeze down to 15 centimeters. So we spread the commissioning this way. Before I go into details of how the commissioning strategy looks, let's say year per year, I will introduce you our main workhorse, the turn-by-turn optics measurements. We have these devices installed around the beam. They are so-called AC dipoles. They are dipoles with quickly changing the field. They excite the beam such that it performs a coherent motion, which we then record with the beam position monitors turn by turn. You may notice here the ramp up of the oscillation amplitude, then plateau, which we actually use for the analysis, and then ramp down. This is to preserve the beam quality. The other technique we use is called K-modulation, where we slowly modulate the strengths of quadrupoles closest to the IP and observing Betatron tune to infer beta functions at the quadrupole location. In the given year, we typically start with the measurements of uncorrected machine. We correct the optics locally around or straight the inner triplets. Then we remeasure again with the local corrections in to calculate and implement global corrections and eventually revalidate. For the simplicity, we did this always without crossing angles, which are normally used in operation to collide the beams only in the interaction point and not everywhere else. So you can see over time, this was relatively stable up until 2015. And in 2016, we need to further constrain our local and global optics corrections by K modulation to preserve the lowest beta function being actually at the interaction point and not somewhere a bit away. In 2017 and 18, the operational beta star got lower, and we needed to include also at the flat top energy the nonlinear corrections, most notably octopolar and sextupolar corrections, and eventually, because of crossing angles, reiterate on the corrections with the crossing angles in. Now I will talk through different aspects of beam optics, the challenges and solutions we found. The linear optics was the only correction commissioned for the collision optics until 2017. Later, we included also the nonlinear part, and this on its own brings many challenges. We need to measure many optics quickly, and also we need to correct the beta star to deliver design luminosity equally for Atlas and CMS. On the right-hand side, you can see typical outcome of our measurements after corrections. This is again so-called beta beating, which gives you a hint of how the beam size develops around the machine. Coupling also changes the beam size. You remember the quadrupoles from the multipolar expansion. If you roll it, you get a skew quadrupole. And this doesn't couple Higgs boson to anything. It couples just horizontal and vertical focusing together. This, of course, needs to be well corrected, mainly because of a lower beta star in high Lume LHC lattice. And in the plot, you can see how the relative beam size changes with the skew quadrupole strength. This, of course, is an imperfection which we are trying to correct, and it's much more pronounced in high luminosity LHC. So up to now, we were limited by precision of these challenging measurement conditions by design. So we can break the left-right optic symmetry to highlight the errors and measure them in an easier manner. This brings me to linear optics solutions. So we developed various methods to measure either beta star, coupling, or all the important parameters on top of the beta functions around the ring from turn-by-turn positions, which may be limited by the performance of newly developed beam position monitors, which should come for the high luminosity LHC. K modulation is for the moment our best method to measure beta star, but this is limited by the tune jitter, which may be fixed if the main dipole power supplies are upgraded. And so knowing this, we are introducing luminosity scans, which help to see where the minimum beta star is, where the minimum beta is in the IP, and to validate the results of the previous two, basically. On the measurement efficiency side, we can measure more optics parameters simultaneously when we do not excite just with AC dipoles, but also with TRF longitudinally. And currently, we are also finding solutions for the machine protection to measure with 3 bunches instead of 1. to gain basically more statistics and reduce systematic errors of measurements. We also, on the short-term strategy, interleave with nonlinear corrections. This brings me to nonlinear optics. On the right-hand side, you can see a sketch of the IP and the magnets. Here you see the triplets, the corrector package up to dodecapolar errors, and then the beams are split. And here you see the crab cavities. We began the beam-based studies at the top energy in 2011, and this led to first interaction region corrections in 2017. But lower beta star dramatically enhances the importance of nonlinearities, and we'll need to correct up to dodecapolar errors to mitigate beam instabilities. This will bring hundreds of measurements, which don't only take beam time, but are also challenging to automate the analysis. For the first year, we need at least, first high luminosity LHC year, we need at least corrections up to octupoles because they are essential for beam time, as you can see on the plot on the left. In red, you see no octupole correction. In blue, you see the lifetime, the fractional surviving intensity after the correction, and it dramatically improves. The other point is that the correction itself improves the quality of our measurements we use for the optics measurements, such as the tune measurement here. You see on the left-hand side with no correction in, it looks relatively poor. On the right-hand side, it's much better. This brings me to the summary. HLLHC will for sure challenge the accuracy and efficiency of beam optics measurements and corrections. But we've already had 2 very successful LHC runs, and we learned valuable lessons there. We developed new measurement methods and prepared the strategies which grows in complexity to adapt to the challenges. And we will use the LHC run 3 as a test bed to improve the further measurements and also the strategies to be ready for high luminosity LHC. With this, I thank you for your attention, and I'm sorry for the technical difficulties in the beginning. Any questions?
Thank you very much, Lucas, and thank you also for staying exactly on time, even with the small technical issues at the beginning. So please, are there any questions to Lucas? I do not see any signs here. So if there are no questions, I have one question. You showed this rather significant effect on the beam lifetime with or without the octopole corrections. Mm-hmm. So what are the main underlying beam dynamics or beam physics effects that are causing this short lifetime if you do not correct?
Well, we essentially lose the beam.
Yes, but do you? I guess you have an understanding of what the main problem is that you correct with the octupoles.
Well, I would say this is a great topic for a rather longer offline discussion. But
okay.
Shortly.
Okay.
Yeah.
Okay. Maybe we can come back to that later. Any other questions or comments from someone from the audience? If not, then I would like to thank the speaker. And please, can you stop sharing your slides?
Yes.
And then we come to the next presentation, which is by Vitek Krasny on the gamma factory path to high luminosity LHC with isoscalar beams. Yes, so the sharing works immediately.
Can you see my slides?
We can already see the slides and we can hear you very well, Vitek. Thank you.
Okay, perfect.
So please go ahead. Just to remind you, please also try to keep the 15-minute speaking time so that we have a little bit of
Okay,
time.
I will try. I will do my best.
Thank you.
You
Please
see, over the last 2 years, we have of the European strategy process, we have spent most of our time in discussing how to answer old particle physics questions with new accelerators like FCC of ILC. And I think it may be refreshing to restore a little bit the symmetry and consider new physics questions, which can be addressed with already existing or old accelerators if you use them in the new way. So this is more or less what I will do in this talk. And the Gamma Factory initiative, which is now being developed at CERN, is going to this direction. And today I'm going to talk to you about one of the applications of the Gamma Factory, which is the application to provide high luminosity LHC, not with protons, but with laser-cooled isoscalar ion beams. In this short presentation, I'm bound to be restricted to general concepts, but for all of you that are interested, you can go to long paper, which is published in progress in particular and nuclear physics, in which you find all the technical details of the scheme. The ongoing high luminosity PP LHC project is actually the largest high energy physics accelerator project which is in construction. And for the cost of €1 billion, we hope to achieve the level luminosity at the level of 5 times the 34 inverse centimeters square and inverse second. So with this advancement of this project, you may ask the following question: why considering a complementary high luminosity LHC operation mode?
One question also maybe to the others. Do you see still the first page, or you see page number 4 or 5?
I see the first page only.
Because I also see only the first page, and it seems to me you are already on page 5 from the slides that I'm looking.
So I'm sharing with you. So maybe the transmission goes very slowly. You see, it doesn't keep up.
It's probably because you went to the full screen mode, and it's probably Zoom doesn't take the full screen. It takes the window of the original. Yes.
So now, so I'm coming back to the.
This is good now. This looks better.
Can you see now my slide number 4? So maybe
Perfect.
Maybe I should come back a little bit. Yeah. So maybe since we have you were listening to me, I will go to slide number 4, which was my last slide. I was asking the question why we should consider a complementary high luminosity operation mode with ions instead of protons. And after all, LHC is a collider of partonic bunches. So why bothering with alternative partonic envelopes? Different way of, you see, putting quarks, gluons, and photons into the beam particles. So to answer these questions, let me consider the respective merits of proton and ion beams for high luminosity research, and feasibility of the proposed new high luminosity AA LHC scheme, which is based on laser Doppler cooling of the ion beams, which can be provided by the Gamma Factory. The principal merits, there are 3 principal merits of the proton beams, and I guess all of you know those merits. First of all, for the fixed magnetic rigidity of the LHC storage rings, twice higher partonic collision energies is accessible for PP collisions. Secondly, the interpretation of the LHC collision data requires an external input on partonic structure of colliding beam particles. And more precise external input constraining at least the longitudinal momentum structure of partonic bunches is available for proton envelopes of partons, mostly because of the fact that Hera and Tevatron run protons and antiprotons. And the third reason is that at present, CERN injectors deliver significantly more quarks and gluons to LHC collision points in proton bunches with respect to ion bunches. The merits of the ion beam are less known and needs to be exposed, you see, because they very often escape, you see, for most of the audience, especially since these merits become important only in high luminosity phase of the LHC. So first of all, ions, contrary to protons, are the bound states of both protons. There are Z protons and A minus Z neutrons. And protons and neutrons have a distinct charge and flavor structure. So the choice of the ion beam allows to tune the flavor and the charge structure of partonic bunches. This is very important, especially if you go to a special case of isoscalar ions, those that have the same number of neutrons and protons, for which you restore the isospin symmetry. So you can collide the bunches in which the isospin symmetry is restored. And for those beams, the partonic emittances, both longitudinal and transverse, there is no need that they are controlled by external data, but they can be fully controlled by the LHC data alone. So the LHC becomes self-sufficient in terms of interpreting to high precision in terms of partonic language of its data. So this leads to significantly higher precision in measuring electroweak processes by using isoscalar ion beams rather than proton beams. And this is nothing new, since the rise of the standard model in 70s and 80s was associated with the fixed target experiment on, say, either isoscalar targets or close isoscalar targets, like for example, iron. So this is something that you see, it's obvious for those people that remember the time of the first test of the standard model. There's another point which is very important. As far as electromagnetic interactions are concerned, and those interactions are not like UCD confining interaction, protons can act coherently within the ions. And this coherent action gives you a Z to the 4th power leap in the photon fluxes. So if you can run high luminosity LHC with ion beams, you have the exclusive access to the exclusive Higgs production in photon-photon collision. In some sense, you have the hadronic collider, but you produce the Higgs boson in similar way like in electron-positron collider. And this is totally unreachable for the PP colliding mode. The next one is totally unexpected. So, and it's a little bit brain twisting, but you see, I can explain this if you ask me the question. You actually expect lower pileup background at equivalent partonic luminosity when you run ions and not protons. And last but not the least, I would like to mention that there are a full number of new research opportunities, especially in the electroweak sector of investigating the behavior of longitudinal and transversely polarized Ws and Zs, which can be opened with the ion beams. So I go to the next slides. But you see, all these merits, you will not profit from them unless you devise a scheme in which the luminosity in a nucleus-nucleus collision would be comparable to the luminosity in the proton-proton divided by A squared. And you see, with the LED runs at the LH, we are very far from this condition. So the question is, can this be achieved at a reasonable cost? You see, no one would say, you see, accept this proposal if this is an expensive proposal. But let's say, if you are prepared to spend, say, of the order of mega Swiss franc, can you actually devise something? And to guide you how this can be done, I present the luminosity formula that all of you know, which comes from the ICHEP and Zimmermann paper, which have the geometrical factors, the frequency of the collision, and all the factors. I rewrite this formula for the fixed interaction region optics and for the fixed bunch closing frequency. And the ratio of the nucleon luminosity in AA collision with respect to proton-proton is just a multiplication of 3 factors. The first are the Lorentz gamma factors of the beam. The second includes the ratio of the number of ions over the number of protons in the bunches squared. And the third is the emittance of the proton and of the ion. The path that I will explore in this talk since the minimal assumption that I made is that I do not want to intervene at the level of injectors. So I basically take the present injectors and do not modify the capacity in terms of number of ions per bunch. So the only possibility which stays in this first studies, you see, of course, it would be much nicer to optimize both the second and the third factor. But for the moment, let's forget about optimizing the second factor. And I will try to explain you what gamma factory can do in terms of reducing the emittance of the ion beam with respect to the emittance of the proton beam to restore the symmetry in between the collision of nucleons, which are confined in nuclei with respect to the collision of protons. So I should tell you what is gamma factory for those that do not know. In short, gamma factories are all the physics opportunities which are provided at CERN with the existing infrastructure. If you inject not particles into their storage ring, but atomic beams, and if you shine the photons on those beams. These opportunities involves using the accelerator as a large and moving atomic traps for precision atomic physics. It can profit from the seventh order of magnitude increase of the flux of the photons, and also in terms of production of secondary particles. And one of the studies that are ongoing in our group is the study of the application for the muon collider. At present, this group is quickly growing. We are now 80 physicists from 33 institutes. So I use this transparency to invite everyone who is willing to contribute to this initiative. But today, you see, even if gamma factor research potential is huge, both in particles, in nuclear, accelerator, atomic, and applied physics, and in terms of opening new research domain, I will concentrate on this one aspect, which is the beam cooling. So now this brings me to the beam cooling question. The beam cooling is actually something that we do not invent. We just adapt the beam cooling techniques from the techniques that were developed in atomic physics and which drove several Nobel Prizes. And you see, if you look at the left side of my plot, imagine that you have a trap in which you keep atoms, and imagine that you have 6 red detuned laser beams sent to this assembly of atoms. There are several possibilities, you see. Since the atoms will move with Maxwellian velocities, a stationary atom sees the laser neither red or blue shifted and does not absorb the photons. I remind you that the width of the cross-section for absorbing resonantly the photon is very narrow for atomic states. Also for atoms moving away from the laser light, they would not see the photons. So the photons will be seen only for those atoms that happen to move towards the direction of the laser. So if you shine the laser from all these sides, then basically starting from the trap in which you put the atoms in the room temperature, you can reduce the room temperature by 6 orders of magnitude and go to the temperature of microkelvin. So the Doppler laser cooling of the ion beams starts from the same scheme. The main difference is the following one. First of all, you have very fast, you see, atoms. So this is not the stationary, you see, your trap is not stationary, but it moves over the circumference of the accelerator with large gamma factor. This large gamma factor is very important because it can make up for the, you see, even for the deeply bound electrons, for the low wavelengths of the laser light that you would shine on this atom. The basic cooling process is very similar. So you basically excite the atom, and then you wait until it de-excites more or less in the uniform, in the rest frame way. And if you are not, if you do not want to bother on all this atomic physics, you see, then I will use the analogy to the cooling mechanism of electron beam. And this laser cooling mechanism is similar to that of the synchrotron radiation cooling for electron beam. The most notable difference is that while the latter is a spontaneous random process, the former, the one that we are going to use, can be stimulated and precisely controlled by suitable tuning of the laser pulse parameter, such as the power, the wavelengths, spread and offset, the photon transverse spot size, and the offset with respect to the ion beam spot. So this allows to selectively manipulate with an extremely high precision a fraction of ions within their bunches with unprecedented precision. For example, you can get out of this cooling process, which lasts typically a couple of seconds, the beam which has, you see, a given transverse side, a given longitudinal size, you see, a given spread of the energies of the particles within the bunch. So I show one example of the simple laser, you see, setting, which gives you the damping of synchrotron oscillation. And you see that for the setting of the laser light, which basically allows you to interact only with the ions which move towards the laser light in the rest frame of the bunch, you get the damping of the synchrotron oscillation over something like 400 revolution cycles. So the conceptual scheme of the beam cooling is extremely simple. So what we propose is to leave a couple of electrons attached to their parent nuclei in the SPS accelerating phase. Let me remind you that in the canonical way of accelerating ions, all electrons are already stripped off, you see, the remaining one between APS and SPS. So then you cool the atomic beams with spatialized laser system at the top SPS energy to reduce its emittance, both longitudinal and transverse cooling. And then the electrons are no longer needed. You just needed the atomic structure in the SPS up to the top energy. Then you strip electrons, you go to the transfer line, you accelerate and collide these fully stripped ion beams in the LHC. So conceptually, the scheme is very simple, but you see the devil, as always, is hidden in the details. And if you look at the present, you see a ion scheme of making ions and accelerating them up to the LHC. There are several, you see, showstoppers or constraints that you have to handle when you devise a really functioning scheme. And those are the question of the existing ion source, which is the ECR ion source. Then you have to beat the space-time tune shift limit in the early acceleration phase. You have to devise a spatial electron stripping pattern. You have to take into account the laser constraint, most notably the constraint which comes from the reduced, you see, wavelengths limit of the laser that you can buy from the shelf, you see.
Just
and
3 minutes left. Huh?
Can I continue?
Yeah, 3 minutes, please.
Okay. So the lifetime of atomic beams, and there is a very important question of intrabeam scattering, beam collimation, beam parameters, and also the parasitic beam burning at the collision in the LHC. So after trying several ways and several ions, we found that calcium plus 20 beams turns out to be the best candidate for this high luminosity AA LHC option as a parton carrier. And this ion is isoscalar, so it would provide all the goodies, you see, of having the isoscalar symmetric beam. And also it maximizes the photon-photon luminosity in AA collisions. So this is the scheme. You see, you start with the ion source, which is very easy to change. You basically change the rod of the lead into calcium. Then you send what comes out of the source is calcium plus 17. It is lithium-like calcium, which has 3 electrons. It goes to Lear, then to PS. It goes to SPS. We use the 2s to 3p12 1/2 transition to cool the beam. And then we send this beam to the LHC. So if you go with this exercise, include all the constraints on the pre-acceleration stage, then you find out that you can collide this beam at the LHC with hadronic cross-section, which is almost comparable to the total cross-section, which is new with respect to lead. And then for the number of ions per bunch that you can drive in the scheme of 3 times 10 to the 9th, you can increase the luminosity up to the value of 4.2 times to the 34 if you keep 50 nanoseconds the distance between the bunches. What is important is that for this luminosity, for proton-proton collisions, you have something like 200 interactions per bunch crossing. Here you would have 5 interactions per bunch crossing. So so this is the simulation of the laser cooling. We just use the full, you see, dynamics of the SPS beam to simulate the cooling. What is very important to notice is that the cooling time, the transverse cooling both in X and Y, it's very fast, you see. The reduction of a transverse XY emittance to factor 5 can be achieved in 9 seconds. So this is sufficient even with the present vacuum of the SPS to cool the beam to the requisite level just to arrive at this luminosity. Of course, we could cool much, you see, we could obtain the beams of lower emittance, but then we run the problem of IBS and also of beam parameters. So this is the, so to say, the golden rule that we stopped at the emittance of the order of 0.3 millimeter milliradian. So my last but once transparency. All what I'm saying is not a science fiction or just the studies. We have proposed an experiment, the Gamma Factory group proposed an experiment for SPS, which has one of the important points, the experimental proof of the proposed cooling scheme. And this experiment would be the first ever experiment that would put Fabry-Perot cavity, which you see on this picture and also with the mechanical drawing, into the SPS beam. And we hope that the Gamma Factory proof of principle experiment, which costs of the order of 2 million Swiss francs, could open a complementary path to high luminosity LHC with equivalent or perhaps even higher partonic luminosities. I remind you that we'll be operating at a given partonic luminosity with much lower background of soft particles in the Atlas and CMS trackers. So there will be not such a strong limit, you see, of what the trackers can handle. And this is by storing quarks, gluons, and photons in bunches of cold nuclei rather than in hot protons. So my conclusions are the following. The high luminosity LHC with laser cooled isoscalar ion beams appears to be an attractive option to significantly enlarge the research potential of the LHC collider. The studies that we have conducted in terms of simulation studies suggest that we can reach already without the modification of the injector system of the ions at CERN, the luminosity which is comparable to the luminosity that you get for the PP mode under the condition that this luminosity has to be leveled such that the experiments can use this luminosity. And to me, the optimal running time sharing would be to spend 2/3 of the running time for PP mode and 1/3 for AA mode. And this is of particular importance if no phenomena are discovered over the initial phase of high luminosity PP operation. Imagine that you run for 2/3 of the foreseen time and you don't see anything new, then say, instead of, you see, adding a little bit of luminosity, it would be much better that you switch to another mode, which would bring a totally new vistas, you see, into this game. The proposed scheme, of course, requires further studies. You see at the much more detailed level, especially on intra-beam scattering, on beam collimation, beam stabilization, head-tail instability, tune shift, beam limit, and of course, as I mentioned, the experimental validation by the Gamma Factory group of the laser cooling simulation. I would like to stress that the successful demonstration of the capacity of CERN accelerator complex to produce, accelerate, store, and cool atomic beams can open new research opportunities in many branches of science, not only for the LHC physics. But also, I would like to mention that this scheme provides also a new way, if you would like ever to maximize the partonic luminosity at the future high energy frontier colliders, because then you can switch the cooling phase. Imagine that you use LHC as an injection to FCC. If you cool the beams at the top energy of the LHC, the limits which is dominant for our present scheme, which has come from intra-beam scattering, are lower by the ratio of the maximal gamma in the SPS with respect to maximal gamma Lorentz in the LHC. And you can actually cool the beams to much higher degrees and obtain the beams of the shape in terms of the length and transverse size and the momentum byte that would be the most suited for high luminosity operation, for example, at the FCC. So I thank you very much for attention, and I'm waiting for the questions.
Thank you very much, Vitek, for this very interesting, inspiring talk and proposal. Very nice. Please, are there any questions or comments? Please just move ahead. Huh?
Dr. Kazanetsky, Sevasakle. Fascinating, Vitek, but I am still puzzled how you get a pilot parameter of 5 at a luminosity of a few times 10 to the 34.
How you get the number of interaction per bunch crossing?
Yes, so low at such a high luminosity with so few bunches. It's only half of the number of bunches on top of it.
Sure. Now, you see, the point is that the difference, and this is something that we have to imagine, the scheme in the luminosity is in terms of partonic collisions. The difference between the scheme of interacting ions and protons is that each proton is used only once. You see, if you count the number of binary collisions, if you use the proton, you use it only once. And here you get similar number of nucleon-nucleon collision, but each proton which is coming in the ion comes, you see, in the ion. So it will propagate through the nucleus, and it will interact several times. So if you count the number of nucleus-nucleus collisions, then the number of collisions of nucleus-nucleus is of the order of 5. The point is that the multiplicity of such a collision is much higher than the typical multiplicity of proton-proton. So this is why at low luminosity, it was preferential to run 30 interaction per bunch crossing with protons and not having the configuration in which you collide two ions and you get either no interaction or sometimes you get, I don't know, 20 binary interaction of nucleons in the nuclei. So if you go to the high luminosity scheme, this is no longer true because it doesn't matter, you see, if those nucleons are bound in the nucleus or whether they are free. The gain in terms of soft particles is a very nice phenomenon which is related to QCD, which has to do with the fact that when the protons enters the nucleus, it loses its soft or weak in the Bjorken, you see, language partons at the surface of the nucleons. It preserves all the hard partons, which are responsible for electroweak and beyond some other processes, but you produce only the background particle once at the entry of the proton to the nucleus. So this is why you have lower number of nucleus-nucleus interaction per bunch crossing, those interactions which have larger luminosity, but if you go to high luminosity, and if you count the average number of, you see, soft particles per collision, the ions are still preferential. There is another point. If you have the exclusive processes involving collision of photons, you can observe them only if you go with nu close to 1, because you should not have the background of 2 collisions in one batch crossing to use exclusivity of 2 photon interaction, which gives you exclusive on-shell Higgs production. I hope that you see all what I'm saying is clear.
It gets, I have to think about it, but thank you. It gives me an idea of what the issue is.
You see, if you read the paper, then you find out that you see, this paper, most of the concepts which are put in this paper are new. So it's normal that you see at first some of them, some way of the things that you find out are brain twisting. But this is why we were so much attracted to this scheme, because it is just against the common beliefs which are deeply rooted. But you see, they are not.
Thank you very much, but I think we need to stop here, even though it would be extremely interesting to continue, I guess, for hours. Yeah. So I refer you possibly to use the time after the session to go in more details. Huh?
Thanks a lot for giving me a chance of answering this question.
Thank you very much again. Very, very nice and interesting proposal. Thank you. And please, can you stop sharing the screen?
Yeah, I already did it.
And we move onward with the talk by Ji Gao from ICHEP on the CEPC accelerator status towards the TDR level. Please, G, go ahead.
Okay, so can you hear me?
Yes, we can hear and we can see.
Okay, so hello, Mike and everyone. So I will talk about CEPC accelerator, so mainly TDR issues. So the first is optimization design and hardware R&D and siting and civil engineering. So about optimization after CDR, so this is the layout of the CDR, I mean CEPC. So I will not go into the detail of the importance of CEPC, and just to show the result, which is two ring and with one in LINAC of 10 GeV.
Gee, I'm afraid we are still looking at the first slide.
It moves or not?
No, it moves not. I still see the first one.
Oh, sorry. Why? Now it works?
No, now it moves. Yes, now it's good. Thank you.
So I take this as a status. So now it works. I'm afraid if I change a full screen, it's still working. I'm not so sure. The page change?
No, don't use the full screen.
Oh, okay. So so now you see this is the CPC CDR baseline. The booster, no, sorry, the injector, 10 GeV, booster, 100 kilometer, and the collider ring. So the CDR parameter, the key feature is Higgs is 3, 10 to 34, and W and Z, it's not very high because the RF cavities, it's 2 cell for everyone, and frequency is high, especially for because it's 350 megahertz. So after CDR, this is the CDR we submitted to European strategy, and so after CDR we optimize again the Higgs by reducing the beta Y to 1 millimeter, and then the lattice also I will show you later. I mean the hardware, and also for Z we propose a single cell, large growing single cell cavity. In this case, even Higgs we use single cell, so that means we need a higher field. But anyway, this is in the TDR phase. We will try to this higher performance. That means Z is 100, 10 to 34 in that level. But be careful that the RF frequency is different from FCC, which is much lower. Okay, so this is the lattice. We change something for the length of the quadrupole, final quadrupoles, and also beta X and something. So the lattice has been relaxed, and in terms of dynamic aperture, and also many errors has been put into the simulation, and for the CDR case is okay with the errors. So this is the RF system, and so here you can see if CDR, you can see this is two cell for everyone. So this is the philosophy is the same hardware for the different energies. But for the TDR phase, we try to push the technology. So we use a single cell for the 3 energies. So the field, you see the red is very high, 40, and the Q is very high, 3, 10 to 10. So we try to use, later I will show you the R&D result, but this is just a requirement. So in this case, the Z can have higher luminosity because of low Harder mode and the wake field and all these things being loaded. And IMDI. The IMDI is, so the 7 meter, the L star is 2.2, and the angle is 33 milliradian. And So this is a important thing we are working on. I will show you the result later. So about the booster, of course, you know, this is from 10 GB to 120, and we optimize the booster parameter and to make it feasible to be off-X injection. So in this case, we can work both on-X injection and off-X injection. And this is the lattice. So if you look at that here, the green one is the so-called, this is the booster, is outside the collider, the detector. So the distance is, so we have some stray field of detector, but this can be corrected. So we have checked, no problem. And this is the cryogenic system for the RF, because we have in the RF in the north and the source pole part, I mean, to avoid the field, the direction of the Earth field to be parallel to the cavities. So we put on these two RF in the north and source, and each side there are two stations. So totally there are 4 these kind of stations. And so about Z-pole, and we are working on the self-polarization. So this in collaboration with BMP, and so it works just for energy calibration with vertical polarization with undulators. And about horizontal, I mean the longitudinal colliding polarization. So we're working on that also. So in the booster, we put Siberian snake. And so this is the intermediate study. I will not go into the detail. So about the injector, this is very conventional, 10 GeV. And so satisfy the requirements of the booster. So this is the damping ring. And the RF is a normal conducting fast cell. And we checked everything, it works. And so to increase, but this is not baseline, but we try this as an alternative. We put a plasma booster after 10 GeV to boost the electron and positron to 45 GeV. So this is the scheme. So I will not go into the detail. So anyway, this is the electron to accelerate electron and positron to 45 GeV. So this is the final focus parameters, and I will not go to detail, but R&D will follow this. Why it doesn't move? Why? Oh. Okay. So, okay. So this is the beam pipe in the interaction region, and so the radius in the barium beam pipe is 28 millimeter. So this is CDR. So right now we are checking that by calculating all the Harrod mode power on this region. And about TDR, I have to be quick. And so you see, this is the item. I listed almost all, but not complete. The klystron, surely, and dipole booster, and cavities, and dipoles, and dual dipoles, quadrupoles, and also vacuum system, collimator, LINAC, and all these things. So I will not go to detail. You can see the list of R&D items. So I will show you the detailed progress. So about SRF, and we have a test model, CDR type 2-cell, and the 2-cell in this one. So in the CDR design, there are 6 2-cell cavity inside. So so they will be tested, and the single cell fine grain we reach the very high field, and also high Q. So about the single cell cavity, we use large grain. So this is Chinese produced, Ningxia produced a large grain cavity. I mean, no, we fabricate cavity, but they produce the material. And also the single cell, 9 cell 1.3 gigahertz cavities, and also we work on the new process of, surface processing, and obtain very good results. And about the 2 cell 650, they already reached the CPC specification. So we are working on a single cell now, which is more difficult, 40 MEF per meter, which is very hard, but promising. So other components, these couplers, and you see the testing couplers, and also the new lab. So I will not circumvent the new lab. It will be finished soon. So the klystron, so this is, we're working on high efficiency klystron, and you see the first klystron has reached its design goal. No, it's not a high efficiency, it's the efficiency is the design is 65, it's reached 62. So the next two will be really high efficiency. One is 79, another is 80.7. 80.7 is multi-beam. Another almost 81 is a single beam, but high voltage one. So we have finished first one, and then next year, at the end of this year, we finished another, and the end of the 21, we finish multi-beam klystron, which is really high efficiency. It's about the how to say, the boosters. No, sorry, the collider ring and booster magnets. So you see, this is the collider ring dual aperture dipole, and which just finished review and will be constructed at the end of this year. And for the dipole booster, you know, this is very hard because of low field. But anyway, we try two types, one with ion and another without ion. This is air core. So this is, but this one, the without ion satisfied the design requirement. And now, right now, we are working on a real long model. I mean, this is the real one, 5.1 meter long, and will be finished at the end of this year. And the left part, we continue to study because not yet reached the design goal of the ion. The separator, electromagnet separator in progress. The vacuum system, so you see this 6 meter long copper and aluminum vacuum system is underway, fabricated and coated, and the superconducting quadrupoles. We are working on to fabricate 1 meter test superconducting magnets with high field, more than 100 Tesla per meter, and this is a winding machine, and this is other things. I mean, for the sealing and coil heating, something like that. This MDI issues, and this is assembly, and this is assembly process, and then we use something very similar to KEK, Super K, and this is collimator, and this is the LINAC components. We have the high field LINAC completed, tested, and positron source tested, and also this is sled, but a sphere sled. This is tested, new one. This is a new one. Also for the cryogenic plant. So we are here. So in several years later, we will have these almost 20,000 watt at 4K. Which we need 4 of this type for CPC. So the laser plasma will be tested in Shanghai at the end of this year. That means surely we hope in November we got some results, but only for electron. But for the positron, we need something like a facet 2 at SLAC.
Okay. We have just 2.5 more minutes, huh? Please.
Yeah, I finish. The side, we have 6 sides. And so now you see we have north side, which is cold, 6-degree average every year and a whole year, and a very extreme source, which is hot. So we have 6 sites. And the civil engineering, so we have the 3 companies working with us and for different sites, and with beam simulation. And so this is the interaction region, and this is plan. And so the critical point is the equipment installation, 3 years. So it's very critical with alignment. So we are working on that to make it feasible. So anyway, this is the scale. That means we want to finish around 2030. This is our plan. So the summary. We are still working on optimization on the design and the hardware. It's really we want to finish before 2023. So you see the progress and the siting, civil engineering progress well. And really we need a young generation and young scientists worldwide to join this kind of project. Thank you very much.
Thank you very much, Yi, for this overview talk. I think everybody's impressed by the progress that is visible in the prototyping of various elements. Are there any questions? We have a few minutes, please. Just go ahead if you have a question. No questions from the audience? If not, I have one question to you because you showed the rather ambitious schedule technically. Can you say a few words about the political situation? Because I remember there was always the plan to enter in a 5-year plan. There was competition with some other largest scale science project. How has this all evolved and how is the present situation looking like?
Okay, so I think the big event is at CERN. I mean, in Europe, this European strategy is very important. And we, Chinese scientists, high energy physics, we echoed very vividly and supporting this European strategy. And we're working very hard on snow mass and in progress. So this is scientist reaction. And at the same time, we feed back to government to the most and to anyway, in the media or internal reports and tunnels to inform them that international, especially European strategy, this is the first thing we got at hand. And also IOC, so the pre-lab is working on, I mean, is progressing well. So the next year, in 1 year, pre-lab of IOC will be established. So this is our goal is to put this CPC inside this next the 5-year plan, which is starting from next year, the 14th 5 plan. That means we hope CPC can start within these 5 years. So for the moment, as for new thing, I mean, the new thing from the government officially, of course, there is nothing, but due to this coronavirus, China government really recently produced, I mean, so-called the infrastructure new plan. I mean, to put many money on the infrastructure inside. And also promote the economic circulation within China. I mean, because of international uncertainties, so many stimulating method to make. Yeah. So this is something new. I mean,
okay.
Not. Yeah.
Thank you very much. So thank you again for this overview talk. And then we come to our next presentation by Michael Roney on the SuperKEK-B, upgrading SuperKEK-B with polarized electron beams. Please, Michael, go ahead.
Okay, thank you. I just want to check that you can hear me and that My slides are moving.
I hear you well, and the slides are moving. It's
okay, very good. Okay, thanks for this opportunity to speak and describe what's happening with this proposal to upgrade Super KEK-B with polarized beams. As you know, Super KEK-B is colliding 7 GeV electrons with 4 GeV positrons at Bell 2, an upgrade from KEK-B, getting a factor of 40 higher luminosity. These are the beam parameters that were recently shown to the collaboration from the machine group. What we're looking at is measuring or introducing polarization for the electrons in order to measure the difference between the cross sections of the left-handed and right-handed beam electrons. It's the same technique that was used by SLD to measure ALR at the Z pole, giving the single most precise measurement of the weak mixing angle. Now, at this lower energy, 10.58 GeV, we would actually be accessing the product of the axial vector coupling of the initial state times the vector coupling of the final state, and through that, the weak mixing angle. This is going through the gamma Z interference diagram. So what you do need, however, is the precise measurement of the polarization of the beams. So of course you generate the sources mainly right-handed electrons and other bunches that are mainly left-handed electrons, and you have to measure that difference. So this is a new path in the worldwide precision neutral current electroweak precision program. You would get very, very precise measurements of beauty, charm, taus, electrons, muons, as well as the lighter quarks. Just to remind some of us that we did still have a remaining bit of tension after publishing this report in 2006 at the SLD, which was measuring the electron coupling primarily, and LEP, which is primarily sensitive to the B forward-backward asymmetry, had this more than 3 sigma difference. This would be the first opportunity to actually look at this with different systematics and a different energy. The kinds of precisions that we are able to get are in this table here. So this is the value of the standard model vector couplings with the standard model uncertainties. This is the current world average numbers. You can see that for the Bs, it's almost 3 sigma higher than the standard model. And if you get to chiral Bell, I'm calling this chiral Bell, this is this Super KEK-B with polarized electrons, then you would improve the B risk error by a factor of 4, C quarks by a factor of 7, tau would be a little bit improved, muons by a factor of 5. If you get up to 40 inverse autobarns, then you actually get really substantial improvements in tau, muon, electron. But this is from the 2006 physics report. This is the world average value. If you just have 20 inverse autobarns from the leptons, you would have an error that's comparable to the world average now. Another way of showing this is for C quarks, the vector coupling versus the axial vector coupling. And for C quarks, these are the current error ellipses, the 1 sigma error ellipses, the standard model is there. This is the plus or minus error that you could get with this experiment of 20 inverse autobarns. And for the B quark, again, you get substantial improvements in that uncertainty. So with the nice thing about this, of course, is that you're only using this clean leptonic states rather. It's a precision probe of the running of the weak angle. This is the weak angle versus the energy scale adapted from the PDG to add this measurement here and these other proposed measurements and their energies where they would be located. This being away from the Z pole, it of course opens up new physics sensitivities that are not available at the pole, where the pole itself, Z is standard model Z is actually dominating the effects. So these measurements would be at comparable precision, but at a much lower energy scale, sensitive to potential new Z primes above the TeV scale. It can probe pure Z primes that are only coupled to leptons, and it's complementary to searches at the LHC. I'll also mention that it's the highest precision test of neutral current vector coupling universality, where the beam error cancels in that when you're doing these universality tests. So it'd be a very precise measurement if you're looking at B to C couplings, substantially better than what we have right now. So the other thing that with such precise measurements is that you have a unique sensitivity to the dark sector, parity violating light neutral gauge bosons, especially when the Z dark is off shell, so it's not actually able to be reconstructed within the experiment, or if it couples to more to third generation than others. So if this thing is for whatever reason is going to tails, then no other experiment can really see such a thing. Because of the couplings are small, this hidden sector wouldn't have been seen. So this was presented in a paper from 2015 looking at the impact of these parity violating measurements, again looking at the running versus energy scale for a potential dark Z of 15 GeV. Chiral web would be here with a very small uncertainty. So obviously there's global interest in this electroweak program. The LHC experiments, the atomic parity violating experiments are lower energy. The molar experiment at Jefferson Lab, which will measure the sine squared theta effect of below 100 MeV using electrons. It'll have a similar precision. And the next generation of E plus minus, we just heard about the SFC, but there's also the ILC and FCCEE where the polarization is planned. There's also a group of theorists that are working on the standard model electroweak calculations. So this is just a couple of plots pulled from those theory papers. The E plus E minus to mu plus mu minus showing here. The points here are actually KK Monte Carlo overlaid with their calculation. And this is with the BABA scattering calculation. In addition to having the electroweak program, you get improved measurements of the tau electric dipole moment and G minus 2. It would also improve the lepton flavor violating modes from tau to mu gamma and tau to E gamma. This was studied in a Super B CDR. And also it actually gives you some information about dynamical mass generation in QCD. So how do we do this? Well, the goal here is 70% polarization with 80% polarized sources. That's just to remind you, SLC had 75% at the experiment. The electron helicity would be chosen randomly pulse to pulse by controlling the circular polarization of the source laser, illuminating a gallium arsenide photocathode. We vertically inject the polarized electrons into the high energy ring. It needs a low enough emittance to be able to do this. Then you rotate to the longitudinal before the IP. And then back to the vertical after IP using solenoid and dipole fields. Using Compton polarimeter, you monitor the longitudinal polarization with better than 1% absolute precision, higher for the relative measurements. So this is needed for the real-time polarimetry. And then you can use tau decays to get the absolute average polarization at the IP. So this is basically this is shown schematically here. This was from Oncope and company at Butker that were involved in these studies. So here's a spin rotator to the IP and back again. You can again schematically see how the spins are aligned longitudinally. So what are the hardware needs? Well, you need a low emittance polarized source. So the current machine is designed with a 4 nanocoulomb bunch, 20 milliradian vertical emittance, 50 horizontal milliradian horizontal emittance. So this is what our demands are. This current focus of work, in particular at the Hiroshima group, is on a gallium arsenide cathode with a negative electron affinity surface. And they're showing they can get 92% spin polarization with a 1.6% quantum efficiency. There's other group working on ILC sources that we can use to leverage in this area. Then there's the spindle rotators that we need. So this is solenoids and dipoles plus quadrupoles needed for decoupling on either side of the interaction group, and these are the groups that are involved in that. In the preliminary studies, one concept of Uli Vinen's at Argonne is to use a combined function magnet, which would replace 3 existing bending magnets on either side of the IP. These are the studies just summarized here. This is the beta functions and the dispersion plots that he has from that, looking at the left side of the SuperKEK-B interaction point initially. Just to, these are the kinds of fields that are involved. So we're looking at being superconducting. And, at Brookhaven, there's expertise in the construction of direct wind magnets would be suitable for these magnets. Another concept is to install spin rotator magnets in the drift regions. This is the Butker group doing this. And so they would be located here and here. And again, this is showing how the spin is oriented with at the 7.15 GeV. This is the beta functions and the dispersion plots around the region of these spin rotators. So they lattice functions are for the left side of the spin rotator, and the solenoids are in orange, and these are the quads, which should be ruled antisymmetrically. Also reported by Yvonne, the depolarization time, that's this red curve here, is here, the sweet point is 7.15 GeV, is roughly 2 hours. I'll just note that when we're topping up, we're operating the accelerator top-up mode at roughly 50 hertz continuously, so we're continually topping up the beam. But if you stop topping up the beam, then the current beam time would be roughly an hour. Also, we have a Compton polarimeter hardware need. So the space is available outside the cryostats for the final focus quad. There's the group at Orsay in Manitoba are looking at that. The Orsay team has had experience with the Hera Compton polarimeter, in particular laser beam polarization. And the Manitoba team has been working on the Compton polarimeter Jefferson Lab Q-week and molar, in particular using this technology, HP Van Maps, as a Compton electron detector. And they've been doing calculations for coincidentally the same energy that we are looking at, 7 GeV. But one of the other things we have in this E plus E minus environment is the tau polarization as a beam polarimeter. Here, this is gives you a sensitivity on the polar angle of the taus is linearly dependent on the beam polarization. So that's basically the polarization forward backward asymmetry gives you the beam polarization. We could get 0.5% absolute polarization at the interaction point, which would include all transport effects, luminosity weighting, and any stray positron polarization. Of course, the advantages here is that you're at the IP, and the biggest uncertainty with just the Compton polarimeter is likely how you transport the measured polarization at the Compton polarimeter to the IP. So this method with the tau polarization automatically incorporates, well, it is at the IP, it also automatically incorporates the luminosity weighted polarization measurement. We know from our experience at LEP that we can get 0.2% systematic error on that. I have a student who's actually exploring this at UVic. It looks very promising, and he's doing direct measurements of the measurement of the beam polarization with tau events with one tau going to a pi and the other is tagged as a row. And we're using the pion for the polarization measurement. And with the half an inverse Atabarn, we're expecting about a 0.5% statistical error. So there's a growing interest and growing international collaboration of accelerator and particle physicists and theorists, experimentalists, half from outside of Bell 2. The group is preparing a white paper as a basis for a letter of intent. And the idea is, of course, to follow that by CDR and a TDR and hopefully construction. One of the attractions of this is an opportunity not just for physics, but serves as a real world project to help develop technologies for learning and training for future E plus E minus polarization projects. We would hope to be able to install a polarization shutdown when in 2026 that is already being proposed in the schedule for putting in a new final focus for SuperKEK B, and we're preparing to have this into the next KK roadmap coming up. So just to summarize, the electron polarization upgrade at SuperKEK B would open a unique discovery window with precision electroweak physics, measuring basically all of the fermions that are available with highest precision. We have a unique probe of universality at unprecedented precision, and we also get significant improvements to the tau lepton flavor violation, G-2 and EDMs. It's competitive with measurements at the Z-pole until FCC comes in, but it's at a different energy. So it's also complementary to the lower energy parity violating measurements. You can test the running, probe new physics at the TeV scale, complementary to the LHC, and probe the dark sector. So we're building on international partnerships with KK to create this unique discovery machine. And by opening this unique window on new physics, we could really find something exciting. So thank you for your attention, and I'd invite all of you to consider taking the plunge and joining this SuperKEK B electron beam polarization project. There's many areas where new people can have an impact. Additional accelerator physicists, experimentalists, and theorists are very welcome to move through the white paper stage. So just this lists the work that we have ahead of us, and certainly more people are very welcome. Thank you.
Very nice.
Thank you very much, Michael, for this indeed very nice and very interesting and inspiring talk also. And as you had here on this last slide, I think it's of big interest for many people from different areas of the community. So perhaps there are any comments or some questions on this talk from the audience. Please go ahead.
Alain? Yeah.
Yes. Hi, Mike. This is great stuff. I didn't see the plot of depolarization. Can you go back to it?
Yeah. Here.
Yeah, this one. Does this include the beam possible beam depolarization?
That's a good question. Yvonne is actually on the call here, I think. I thought I saw him. Yvonne, can you answer that question? Does it include beam?
Yes, I hear. I expect that beam will be not very strong because the spin tune is far from the Betatron tunes. So no resonances from the beam can damage polarization.
Okay, so it will just be down to the beam lifetime.
Yeah, and so this is actually longer than the beam. But, of course, the beam lifetime is not an issue here because we're continuously topping it up. So at 50 hertz, we're putting in new polarized bunches.
Really, beam lifetime will be much shorter than 1 hour. It will be a few hundreds of seconds only. So the polarized beam should be renewed every, say, a few hundred seconds. And that could also help against the depolarization processes.
Right.
Yeah, what I put here is just what the current lifetime is that we've been seeing when we turn off the continuous injection.
Okay.
Any other comments or questions? If not, then I would like to thank you very much again for this nice presentation. Thank you.
Yeah, thank you.
Can you stop sharing your screen? And then we move on with the next presentation by Alain Blondel on circular versus linear E+ E- colliders, addressing the aspects of complementarity between these two approaches. Alain, please go ahead. Yes.
Thank you. Do you see my screen?
Now it's black. Yes. Yes, we see it.
Okay, so today I will discuss the question of complementarity between linear and circular E+ E- colliders. This is based on a paper we submitted on the 26th of December of last year to the strategy. The motivation is that all these colliders at the electroweak scale have been called Higgs factories, with the underlying assumption that probably one needs only one of those. And of course, that drives the proponents of linear colliders or circular colliders in a state of protest that they can do many things than the other cannot do. And in fact, that is correct. This is a bit dramatized by the very strong synergetic link between the FCCE and the FCCHH, which is really the only way to get a favorable funding, and it increases considerably the physics case for the 100-kilometer tunnel. So this is considered the best possible scenario by the FCC collaboration. So the question is, will the FCCE or CEPC, while enabling 100 TeV proton-proton collisions, kill the linear collider, or vice versa? Will the ILC kill the FCCE and therefore FCCHH? So we've wanted to get over that problem and investigate the physics differences and the complementarity between these machines. People have been talking about competitive comparisons, but it's really more creative, more positive, and to go and look what they both do that the other doesn't do. So replace FCCE or ILC by CPC, click if you wish. The remark was made long ago that because of the very different energy dependence of luminosity, these machines have to be complementary. That was already done in 2012, and this is a slide I showed in 2014. The operational differences are quite clear. The luminosity plot you have already seen. This is confirmed by the plots in the briefing book. The consumption is slightly different plot, but it says sends the same message. And basically, for efficiency reasons, you would like to run a circular machine up to 350 GeV and pick up with a linear one above 350. If you take the 250 GeV point, for instance, it takes 9 gigajoules per Higgs to produce a Higgs boson at the FCCE. 9 gigajoules is about 3 hours times a megawatt. And it takes 50 gigajoules at the ILC. And of course, this changes. And again, if you want to go higher in energy, at some point, you will want to move from E plus E minus collisions to muon colliders. The beam polarization in the circular machines, you like to, or you prefer to have transverse polarization that gives you very high precision energy calibration, while in the linear machine, without too much effort, you get longitudinal polarization for the electrons, maybe for the positrons, and that gives you additional degrees of freedom, as Mike showed for the bell in the previous talk. The long-term energy upgrade is clearly the circular machine leads to a proton collider, like lab to the LHC, while the linear machine can be expanded by excavating more tunnel and adding more cavities. They can make several interaction points in a circular machine and just one in the linear machine, unless you have a push-pull system, which reduces the luminosity per interaction point, unlike for the circular machine. The run, this is one little point which is important to keep in mind. When you put a circular machine in a circular tunnel for E plus E minus, well, you know a hadron collider is going to come behind, so you better be efficient in your running because it will be of limited time. While for the linear machine, it is extended to the extent that you get funding to run. So coming to the science, the most important thing to look at, of course, is the Higgs factor A. And if you just look at the first stage, what these machines do is they take the LHC measurements, which require total width assumptions to make sense of them, into a model-independent measurement, because you measure E plus E minus going to ZH. And that measures the Higgs coupling to the Z in a way which is completely model independent. So this is expressed in this table where you see typically the first 7 to 12 years of these machines. And you see that the precisions are within a factor of 2. They are indeed similar. For all these measurements that are special to the E plus E minus machines, which are up there, while the measurements which the LHC can do much better are those which are the rare couplings, because these require a very large number of Higgses produced, which is not available for the E plus E minus machines. So as you can see, this first step basically has two functions. It provides a model-independent interpretation of the LHC results, and in addition, it provides measurements at the percent level for many things. Now, the circular machines still will have more statistics. They will do this in less time. The fact that there's a precision program at the Z helps. And in this particular case, the longitudinal polarization doesn't help that much if you combine with HLLHC or if you add information from a Z-run. If you go to the higher extrapolation of these machines, there the conclusion was very clear. The combination of FCCE and FCCH is unbeatable, partly because again, the Hadron Collider with 10 to the 10 Higgses is going to produce very high precision measurements of the mu mu, gamma gamma, z gamma, TT bar, and self-coupling. Let me come to another piece, which is completely unique for the FCCEE, is the possibility to measure the electron Yukawa coupling. Now, that requires setting the machine to 125, whatever the exact Higgs mass is, and that will need to be known to 5 MeV or better, basically the Higgs width, from the 200 GeV run. Now, this is under study for the FCC. The CPC have already done an analysis where they show that they can measure the mass to that precision. You need very high luminosity because, as you see, the cross-section is a fraction of a femtobarn. You need monochromatization, which you can do because the two beams are in different lattices, so you can do the monochromatization using magnets and not, as in LEP, it would have necessitated electrostatic separators. So this is much more convenient, but this needs to be done in practice at this point. So this is quite work in progress at this moment, and therefore I'm very happy to talk to an assembly of accelerator physicists here. Continuous monitoring and adjustment of the center of mass energy to a precision of an MeV, and that we can do with the transverse polarization calibration. And of course, you need, the backgrounds will be quite large, so you need a very sensitive event selection against backgrounds. So this is being studied, but clearly you can go much better than even the FCCH will ever be able to do with this research. Now, we talked about longitudinal polarization in the previous presentation. Now, most of what you see in the PDG from polarization in E+ and minus colliders concern the transverse polarization and the ability to measure the beam energy very precisely. Now, with that technique, we think we can get to about 100 keV precision on the Z mass, so it's precision of 1 per million. Similar precision of 25 keV for the Z width, and also the weak mixing angle. Michael, we are here a factor 100 better than the ALR from SLC. And alpha QED we can get from the slope of the forward-backward asymmetry versus energy with a precision of 3⁻⁵. So this is really something completely unique. This precision measurement might seem to be boring, but or just insect collecting, but they really are sensitive to new physics. We saw that at LEP with the predictions of the top and Higgs masses. But you can see this on the right, this plot, which shows the sensitivity of a number of operators for new physics. And you see in red, the electroweak measurements, in green, the Higgs measurements. What is interesting in this plot is that these are not the same operators. So that shows that the Higgs measurement and the electroweak precision measurements are complementary. In addition, the red bars are typically a bit higher than the green bars. So we are really in a very interesting exploration here. So more on the TerraZ. The TerraZ from the FCCEE is also a flavor factory. If you want to go beyond super Keck B and Bell 2, you need to have more than 10 to 11 B pairs. We'll have more than 10 to 12 B pairs. These people come to us and say, we want at least 5 10 to 12 Zs, and that's just what we are proposing. And I made a list of all the measurements you can do. Now, this is a new need compared to the standard Higgs factory because the detectors are different. The requirements on detectors are different. You need particle ID. And so this is a story to be written. Let me come to the new physics exploration. Now, the immediate reaction is that if you have a machine that goes to higher energies, then you'll have better chance to explore new physics. The only difficulty here is that up to 3 TeV in E plus E minus, you're going to go on a territory which has already been explored by the LHC. So there is a chance that there are items which have been missed by the LHC and continue to escape HLLHC or even FCCH8. And there's a number of examples like this. And definitely, if you want to have complete coverage, you need all colliders, FCCE, ILC, and FCCH8. That's what you need to do if you want to put all chances on your side. Dark sector. With the Higgs discovery, we are in a very interesting situation. The standard model is complete. The electroweak corrections work perfectly, so they would be very happy not to have new physics at all, unless it is extremely weakly coupled to the standard model, and that has motivated this dark physics, which is basically new physics, which has very weak couplings to the standard model. Now, the Z run of the FCCE is particularly good for this. The example which made us notice is, of course, the right neutrinos. Neutrinos having mass. You expect that the left-handed neutrinos are right-handed partners. And here we're talking masses typically between the B quark mass to the Z mass, where the range of new discovery potential goes from the present limits of 10⁻⁵ down to 10⁻11. So this is typically 6 orders of magnitude gain. The precision measurements exclude couplings up to very high masses, at least 60 TeV down to 10⁻⁵. So this is really a very specific capability of the Z factory. You can hear another plot for action-like particles. And you can see that the FCCE will explore in that range of masses down to very small couplings, while for instance, the ILC or click will expand to higher masses, but for larger couplings. Now, probably the most strongest argument to keep a linear collider alive is the following. A high energy E plus E minus collider might become urgent, just like the Higgs factory today, if a new standard model coupled particle is found at a hadron collider for which something is missing that needs to be gathered by an E plus E minus machine. We're not in that situation today, but of course, we should keep that window open. And that clearly, ILC or click would cover the high energy E plus E minus in the energy range from 400 to about 2 or 3 TeV, where the muon colliders would become more competitive. So there's a table that summarizes these complementary qualities. I think you can let you look by yourselves. It's very clear what you need to do. You need to run the machine. In each and every range, you want to run the most efficient machine, which is so that between 30 and about 300 and to the top quark threshold, you want the FCCE, and for energies above the top quark threshold, you want the ILC. Conclusions. I think there are significant domains of physics in which either FCCE or ILC is unique. I've listed them here. I'm not going to repeat them. This particular argument of complementarity has been discussed in the strategy, and you find a clear signal of it in its conclusions. The general recommendation is to prepare a Higgs factory followed by a future hadron collider of high energy. And the practical recommendation is here. Europe, together with its international partners, should investigate the technical and financial feasibility of the FCC. Such a feasibility study of the colliders and related infrastructure should be established as a global collaboration. And so we have a few years to do this until the next strategy update. However, the linear collider was encouraged, and it was said that the European particle physics community would be happy to participate. Thank you.
Thank you very much, Alain. This is indeed the right and good moment to stop, and you were staying exactly in time. Thanks a lot. So, are there any comments or questions from the audience to Alain? Please, just go ahead.
Alain, it's Mike here. The on your, which slide is that? I think it's 5. You were talking about having both electrons and positrons polarized. Are both of those required, I guess, if you want to get the energy calibration, right?
You were talking for the for which machine? Oh, for the energy calibration, yes, that's quite important. And the reason is that you need the energies of the electrons and the positrons, and they are in separate rings. So, and to the extent that we know the magnetic calibration to 10⁻⁴, and you want the energy to 10⁻⁶, you need to measure the polarization and the depolarization of both beams.
So what's the technique for polarizing the positrons being proposed?
Oh, this is coming from the natural Sokolov turn-off polarization. We have a set of wigglers to increase the polarization rate, and we think of polarizing typically a few hundred bunches out of the 16,000 bunches in the machine. So at the injection time, you turn on the wigglers until you have polarized a few hundred bunches in each beam, and then you inject unpolarized beams in the other slots.
Okay, thank you.
Okay. Any other question or comment to Alain? If not, then thank you very much again, Alain, for this talk. And we come to the last presentation in this session from Benny Ward. An overview of the path to 0.01% theoretical luminosity precision for the FCCE and its possible synergistic effects for other FCC precision theory requirements. Please, screen is already shared. We can see the slides, and I guess we can hear you in a moment.
Okay, well, thank you very much for the opportunity to present the research that I've done with Stade Gadek, Wieszek Placzek, Maciek Szypek, and Scott Yost. And you see the publication there. And I'll be expanding upon it as indicated in the title to possible synergistic effects with other precision theory requirements. And so this is almost sort of where we are. This indicates we're a little bit better than what that shows there, as I'll say in a moment. But basically, this is sort of with that proviso, the present situation in the FCC EE that Elaine was trying to advocate in a diplomatic way, as you can see, really changes the game considerably. And I want to talk a little bit today about the issue of the number of neutrinos and the luminosity problem that goes with this kind of tremendous precision. As you see, these are the kind of factors that we're looking at, as he indicated briefly in his talk. The QED part of the errors on these shown here in bold, and we need quite some advances in the theories that we've had in other talks today, and we think we can do this job if we get proper support. The main thing that we'll need, of course, a higher order in fixed orders, as well as better resummation and more sophisticated Monte Carlo programs. And as we've heard a little bit in another session today from Giannis, and also as you can read in this paper by Static, the deconvolution needs to be a little more sophisticated because because of this new precision, some of the effects that we were able to leave have to be treated like QED, if you will. They have to be taken into account in order to take advantage of the what we're headed for in terms of the new era presented by FCCEE. If we look on the luminosity, one of the places where it enters is in the counting of the number of quote unquote massless neutrino species. They're not really massless, but almost massless. And at the left time, you see this was the number as I showed earlier. Luminosity enters at, we with VH Lumi out of the box was 0.61%. And if you do some pairs, you can get it down to 0.54 as Opal did. And so it contributed this amount to this error you see here. However, recently, Patrick Deneau and Sadigarik in this paper, which is published, have revisited this matter because we've been making some progress on this 0.61 number. And so, especially Patrick had a revisit to the left data, if you will, and was able to take advantage of the fact that the current LUMI era, just because vacuum polarization has gotten better, et cetera, is down at this level here, you see. We did the error analysis on the experimental side, and that now has the number of massive neutrinos from this approach at 29975 plus or minus 0.0074. And the part of it from luminosity, because of this change that you see here, is now down in double knot 2A. And the question, of course, we should do better at the FCC. We need to drop this down by a factor of 4 more. And as I just explained, that the reason we went down already was because of Jaeger-Leonard's work in the meantime, primarily. I don't seem to have a reference right now, but I do later. Now, so this was sort of the legacy of this problem of the luminosity at left. Here's the 0.61. At left 2, it's somewhat larger, but as expected. And in this recent update, what we see is that from 99 to 218, so this is sort of now vacuum polarization went from 0.040% down to 0.013%, and actually more recently it's down to 0.011%. So this is on Fred. This is on Fred, and therefore we have a current status of 0.037% for the luminosity using BH Lumi. Thanks to Fred. And so for this FCCEE, this needs to drop down by a factor of order 4 to 0.01%. And we can do this. Now, we have to be careful because the acceptance at the FCC is not quite the same as the typical so-called narrow detector at LEP. You see, it's a little wider. And but if we go through the various contributions, and I'll do that in the talk in the time I have. We believe that with proper theoretical support, this is what we have published in this paper, this can be done. If we look at the vacuum polarization, what we expect from discussions with Fred is that we will go down to 0.6 times 10⁻⁴. And that's just an ongoing program of research that he has had now for some considerable time. One of the bonuses that we get in this problem is that we actually calculated more than we put in the program. So if you look in BH Lumen from left time, you'll see that there's the exact order alpha and exact order alpha squared L squared corrections are in there. But if I'm talking photonic, we actually had the formulas for the order alpha squared L corrections. And for the order alpha cubed L cubed, for example. And so the thing that has happened is that because of Fred, the vacuum polarization in pairs are not dominant anymore. You say, well, why didn't we put those other more precise contributions in? Well, because there was no point, because vacuum polarization was sitting there, and I think we had 06 there or something. There was no point to it. And therefore we can now go back and take advantage of the calculations we did to reduce precision further. So if we now put in the, for example, the order alpha squared L, which we did with Yost and Mellies, we already had this. Then the question is adding in the order alpha cube L cube, which we had here. I show the references. If we put that in, then we're missing, instead of missing what we were on the previous transparencies, we're missing order L to the fourth L, order alpha to the fourth L fourth, and order alpha squared L cubed. And so these guys enter at these levels we show here. And so the vacuum polarization, as I indicated, we enter like this. Light pairs, we had formulas for light pairs. We didn't put them in because of the situation that vacuum polarization was big enough. Now we put that in. We know how to do that. You can go through and estimate. Let's say we now go through and put in everything we know. Then we have to look at the photon interferences again, and put in those. The easiest way is to just take BH wide, which has all of these things done to the accuracy required, and extend that out to a CEX type KKMC approach to Babos, in which case those interferences would be down at the 10⁻⁵ level. So again, we didn't do it before because we were dominated by, for example, backward polarization. And you can have a look on what the size of these effects in VH wide. And as you see, you do need to take them into account because they vary non-trivially as you go across the Z, and they're at a level that requires our attention. But VH wide is able to do that, as would be the ZX extension of VH Lumi. So vacuum polarization I already discussed. Fred is, we've been in contact with him. And the main point is, as I'm saying here, there's some imprecise knowledge of the coupling of T-tail exchange. And the idea is to have a strategy where you go in 2 steps, obtaining in the region below 2.5, using dispersive methods, and then using perturbative methods when you can. And it's an industry that Fred has pioneered, and we expect this to be the outcome of that. So if we go to light fermion pairs, as I said, we have those under control. We had 2 different ways of doing that. We had even a version of VH Lumi 2.3 that actually included the pairs themselves. And then there's many approaches to realizing them in addition to what we have in VH Lumi 2.30. So that's not the, that's not expected to be a problem. Again, this is all assuming that we get proper, we know how to do this. This is all assuming we get proper support to do it. That's the main point, I think. And finally, there's the up-down interference effect, which you see in this, especially in this acceptance, we will need to take into account using VH wide or now, because it used to be negligible, and now we will need to either use VH wide or the extension of KK Monte Carlo lobotomies. But that's, again, not any showstopper. The one thing that we need to do in these type of analyses, and when you have Monte Carlo precision work, is so you have all your physics and you have all your Feynman diagrams and all this, and you got it all in there, and you think you've got the ducks in a row, but now you need to be able to prove that there's no bug in it. That is to say that you didn't, in 10,000 lines, have a typo or something. Just as an example, that's not the only way. Now, so that's really, when you get to this type of precision we're talking about with these type of calculations, how do you prove this, what I just said? Now, one way is they have 2 independent realizations of the Monte Carlo. And in the past, we had 2 hybrid Monte Carlos that I show here. And we had the group from Pavia, SOPS PV, which was completely independent. And we could do, therefore, cross checks, and we got 0.27% down for the missing photonic corrections, together with the missing photonic correction that we knew that we didn't put in as the technical precision. Now, when we go to this 0.01 that I have here, we will need a proof that we have technical precision under control. We're hoping that Baba Yaga from Piccinini's group will be developed. He's made talks about that. Maybe he's going to make one in this meeting. That would give us an independent cross-check. But we also can take the view that we use the CEX realizations that I talked about as a cross-check on the EEX, that is to say the original BH-Lumi type of formulation. Professor Friccioni has also entered into the discussion as our Professor Bertoni et al. With these results, which open up another possibility for getting an independent check on the technical precision.
2 minutes left. If you can slowly come towards the end, please.
Excuse me?
We have 2 minutes left.
Okay. I will finish in 2 minutes, not a problem. Now, historically, we move in this direction. And we see that we're moving toward including the CEX for the BABAs, which would mimic what happened with Kikimonic going into hadrons. And so we can do the same here. And CEX BH-Lumi means that we can extend it to the W production as well as the Z and Wannigo BABAs. And we therefore impact synergistically the precisions of things like the forward-backward asymmetry parameters that we've heard about with the CEX study that's been done recently by Jos and Yannick, and threshold reconstruction of Ws, and threshold and the reconstruction of W at higher energy, where you need about 0.3 MeV for FCCEE for the theory error. And again, the CEX extension of the work done at LEP, YFSW3 called W, and Yannick et al. Have already shown the formalism. Here I show how to make a contact with our CEX, our normal CEX nomenclature with what they have in the paper. But I think in summary, since you wanted me to end, you said in 2 minutes, I think I am doing that. We are in a position to realize 0.01% precision, provided we get proper theoretical support. Therefore, that's not a showstopper. And I think that those methods that we've been building on are well tested. The CEX, EEX upgrades of BH-Lumi will give us an independent check on the technical precision if we don't get one from Baba Yaga, for example. But there are no hard obstacles on the way to 0.01% QED precision on the theory side. And if we get the proper support, we don't expect any trouble to do that. Thank you very much.
Thank you very much, Benny, for this interesting talk on precision at FCCEE. Are there any comments or questions from the audience?
Yeah, Benny, what's the timescale for having the BABAs included in KKMC?
Yeah, so again, this is something that depends on resources, so depending on resources, this is a few man years of work, which means that if we had a postdoc assigned to that job with us, it would happen on the scale of years, a year or two or something like that. But we don't have a postdoc assigned to that, so I cannot say when it will happen. You should tell OE that you would like for me to have that postdoc.
I see another question from Alain.
Hello, Benny.
Yes.
Thanks for the nice talk. As I mentioned in my presentation, we are planning to measure the alpha QED of MZ by the slope of the forward-backward asymmetry with energy. Did you plan to include this possibility in your calculations, or?
Yes, I mean, that's what I was trying to show. He made me go a little fast. See, this is the step in the direction you're talking about. This is the delta forward-backward asymmetry. This is if I take the difference of these on one side or the other of points. Right now, this is the error that we've got in this paper that I'm citing here, it's about a factor of 10 larger than what you need for what you just talked about. And we don't see any showstopper to getting that factor of 10, but again, we need resources to do it. I mean, it's a question of putting some time on it, that's all.
Okay, so we've done our campaigning for you, but we need to do more, right?
Well, we didn't get any. I don't have any
Well, that makes it
money to show for your efforts, but I do appreciate them. I do appreciate them. But when we have resources, what you talk about will happen. Yes.
Yes. I think we have another question from Graham Wilson.
Hi, Benny. I've always thought that using the process E plus E minus to gamma gamma could be a similar QED process that can be used for absolute luminosity. What are the prospects for getting that to similar very good precision?
Pretty good. I mean, that's an approach that others have looked into. We have not, but it is a possible way to and if we look into it, I mean, in principle, it can have similar. I can't comment on about the measurement part of it, but certainly on the theory side, there's nothing to prevent similar kinds of arguments to be done for that process.
Thanks.
Okay, since I do not see any more raised hands, I think we are finished with the questions. Thank you again, Benny, for this presentation. So we are through with the 6 talks of the session. I would like to thank once more all the speakers for keeping so nicely the time and for the very interesting presentations and high quality presentations. I would also like to thank the organizers for providing this excellent virtual environment for the conference. And I wish you all that attended this session a good continuation of the conference. Thank you very much. Bye-bye.
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 Danielle, are you online? This is Leah.
Hello, Leah. Nice to hear from you.
Hi, nice to hear from you too.
How are you?
I'm doing good. Here I am. Hi.
Hello.
I
was sorry, you could not hear me. I realized I was answering without.
Okay.
Yeah.
Hi, Daniel.
So
Hi.
I guess we should go through all the talks to test them, right? No?
Yes.
Right. Yes. So do we have all the speakers? One request I have, hi everyone, from the speakers is if you could please state your name. So when I introduce you, I try to be as close to the right pronunciation as possible.
Hello.
Hi.
I think I'm the first speaker, so maybe you can tell me if you can hear me and you can see me.
You're Yaroslav?
Yeah, I'm Yaroslav, yes.
Pasternak?
That's correct, yeah.
Okay, very good. We can hear you and we can see you.
So shall I try to share my slides?
Yes, please.
Okay, I try. Let's see if it works.
Are you from Imperial College London, Yaroslav?
That's right, yes.
Okay.
No, sorry, I have to do here. Okay, let's see. Can you see anything now?
Yes, but it's not in full screen mode.
So that was something I wanted to test, because on the previous session, people have been stuck on the full screen. So I'm going to make a full screen now. Okay, I did a full screen now. Can you see the progress of my slides?
Yes.
So now I'm in the first
it's
slide.
Perfect.
And now I'm on the second slide. Can you see the second slide?
Yes. Yes.
Okay, that works. Thank you very much.
It's perfect. Yes.
So I can now stop sharing and you can test another person.
Great. Thank you very much.
Stop sharing. Yeah. Okay.
Next person is Daniel.
Yeah. So Daniel Schulte. Well, I can switch on the camera, but I will not during my presentation.
So we can. You don't plan to use video, Daniel? Okay.
I can switch it on if you prefer. Okay,
it's up to you.
Yeah. Oh, I can do it. So this is always. I need to do it twice. So. Okay. And. Okay, can you see that?
Yes.
Okay. And it moves.
Yeah. I don't know about others. I see a green frame around the slides. I'm not sure if it's by design or...
No, this is Zoom on Linux.
Ah, okay.
I actually have to start this twice so that the frame is at least around everything instead of in the middle of it.
Okay.
I could do it from the laptop, but then it's not...
But this
the
looks
acoustics
fine,
is very
though.
poor. So if this is fine for you, then I will use this.
Definitely.
Okay. Good. Perfect.
So,
thanks.
Okay, thank you. Very good. Next speaker, Kolamati. And you're CERN, Daniel, right?
Yes.
Yes.
I am.
Okay.
Hi, do you see me? Do you hear me? Do you see me?
Yes, both.
Okay, do you see me? Okay. I am Francesco Collamati. Yeah, it was correct enough. And let me try to share my screen.
I'm sorry, I couldn't hear your name.
Francesco Collamati.
Francesco Collamati. Very good.
Perfetto. Perfect.
Okay.
Now, I'll try to share it. Tell me if you see the first slide.
Just a minute. Yes, perfect.
Does it slide?
It advances, yes.
Okay, okay, very good. I think it's enough.
Okay, excellent, Francesco.
Thank you.
Thank you very much. And then we have Matthew Jones. By the way, Francesco, are you INFN Rome?
Yes, exactly.
Thank you.
Yes, thank you for identifying the name I go by, not my first name.
So how should I introduce you?
Matthew Jones is perfect.
Matthew Jones, thank you, Matthew.
I can try sharing my screen. Just
Purdue, right? University.
Yes, I'm at Purdue. So I think I'm sharing. How does that look?
Sorry, is it my connection that's not so stable? I lost you again for a minute.
It was fine for me. I could hear very well.
Okay, I'll stop my video. I don't think there's much to see, but I'm sharing my screen, so you can let me know if you see it clearly.
Very clearly, yes.
All right, that should be good then.
Purdue University is correct, right?
That's correct, yes.
Very good.
It's not Purdue, it's Purdue.
Purdue, okay. Well, I may have a challenge there. I'll try my best. Okay. Great. Okay. Next, we go to Marco. Marco Romagnoni, or how do you pronounce your name? Is Marco here online?
Probably not. The surname, I think the pronunciation is okay, perfect. I can say it as an Italian, Marco Romagnoni, but he's
Romagnoni. Okay,
Yes.
great.
Maybe we try the next speaker, and meanwhile you could come back.
Okay, and sorry, Marco is, hold on, University of Milan I have, INFN, University of Milan.
I think so, yes.
Okay, good. And then we have Benedetto Di Ruzza, what? How? Benedetto.
Perfect. Benedetto Di Ruzza is here? Not yet.
Okay. Okay, very good. All right. We still have 8 minutes, I guess.
Okay. Leah, just a communication for you. I will not be able to attend all the talks. So at some point, I will have to leave.
Okay, that's fine. I will start the recording as the instruction. Should I do that in a few minutes, 2 minutes before, on my own computer?
Hello, yeah, this is one of the organizers. Yes, me and you should both record the session.
Okay.
Yeah,
Okay.
like 2 minutes before we start. That's fine.
Okay. I'll do that then.
Okay, thank you. Perfect.
Yeah, thank you. Is there anything else? Let's see.
I think it's quite fine. If you want, before we start, you can say a few words of introduction, but if not...
I will say just a couple of words. Yeah. My only concern is if my internet is unstable, is somebody else, Danielle, that can help out? For example, sometimes I cannot hear what the speakers are saying. Can somebody jump in and fill in the gap?
For the first 2 talks, it can be myself.
Okay, and then?
Maybe we can, and then you can give me a feedback if you have really problems. It might be that if you stop your video, maybe you will not have these
Okay.
problems.
I think as soon as I just say, introduce the session, I'm going to stop the video.
Yeah. Yes, perfect.
Yeah. Okay, great. Thanks a lot.
Thank you.
Okay, hello everyone. I'm Leah Merminga from Fermilab laboratory in the US. Welcome to session 11 on accelerators, physics, performance, and R&D for future facilities. So the second block of the session 11 will be mainly focused on muon colliders and muon-related experiments, along with simulations and future plans. We have right now about 19 participants attending this session. Welcome everyone. And I'd like to remind a few details about technical setup. So speakers and participants should mute themselves unless you're speaking. And attendees and participants should first say their name before asking questions when unmuted. And also attendees are kindly requested to ask questions using the raise hand feature. And if this does not work, then you can post questions in the chat box. With this, I would like to introduce our first speaker for this session. And the speaker is Jaroslav Pasternak from Imperial College London. And he will talk about first demonstration of ionization cooling by the muon ionization cooling experiment. Jaroslav, please.
Thank you very much for a nice introduction. I have to say that it's a pleasure to be here, unfortunately not in person. So let me share the screen. You should be able to see my slides now.
Yes.
And I will go to the full screen. I'm presenting a first demonstration of ionization cooling of muons by mice experiment on behalf of mice collaboration. As you know very well, muons as elementary leptons 200 times heavier than electrons are actually an excellent particle for a collider. This is because you can avoid a large QCT background, which is typical in hadron colliders. And also muons are offering a full center of mass energy for creating new states, in contrary to hadrons. And because of their high mass, the emission of synchrotron radiation is highly suppressed, which allows to build a compact collider facility, and also to preserve a high quality beam once this high quality beam is created. And I hope I will give you an indication how that can be actually done. Also, the natural large coupling to the Higgs mechanism is present due to the large muon mass. So that allows for a spectrum of experiments to be conducted. Last but not least, muon beams are also important because of an anomalous magnetic moment, which is an indication of a physics beyond the standard model. Searches for lepton flavor violation, which enables a very good complementary test to the standard model at very high mass scales. And also that they can be used as a high quality neutrino source if you realize new storm or a neutrino factory. So I go to the next slide. And this slide, I think you will see again in this session, is basically indicating the energy at which the cross-section for producing a new particles is equivalent between the muon collider and the proton-proton collider. And it basically indicates that the muon collider with center of mass energy similar to the current LHC is somehow equivalent to 100 TeV proton-proton collider, which I think is very good provocation. So, however, if you start thinking about how to build a muon collider facility, which on this slide I show the schematic how the neutrino factory or muon collider could be realized, you quickly realize the challenges of working with muon beams, basically because muon beam is unstable due to the limited muon lifetime, and also because muons are produced as tertiary beams. Basically, in these facilities, you always need to typically, you produce muons by firing a high power proton beam on the target where pions are produced, and then you capture those pions, wait until the muon beam is formed in the decay, and then you have limited amount of time to cool and accelerate the beam before you can use it. So in this talk, I will talk about ionization cooling technique, which is the only technique fast enough to actually provide a solution for that. And this is the main topic of my presentation. So what ionization cooling actually is basically using the fact that when a particle is passing through the absorber material, it loses energy in both longitudinal and transverse directions, which if you can recover the lost longitudinal component using RF cavities, actually cools the beam. However, there is also present multiple scattering in the material. So if you look in the cooling equation shown below on this slide, you can actually realize cooling by simultaneously having very strong focusing, using low Z absorber materials and having high RF gradient. Then you can actually make the cooling term winning over the heating term. So that's in order to demonstrate this in action, the mice experiment was created, and it was operated at Rutherford Appleton Laboratory between 2008 and 2017, grouping 30 institutions from 10 countries, consisting of more than 100 physicists and engineers, which you can see nice smiling photo below. So the goals of this was to the goals of the experiment was basically to demonstrate high acceptance tight focus solenoidal lattice, where you can integrate low Z liquid hydrogen or lithium hydride absorbers and validate the details of the material physics models and demonstrate actual ionization cooling. So the sketch of the experiment is shown with various components. Beam goes from left to the right, and the absorber is in the middle. I will talk about various subdetectors, which while I go to the experiment. You can also see the mice cooling channel embedded in the shielding, shown in gray in the photograph below. So going to the next slide, the beam was initiated in the ISIS synchrotron at RAL, where the internal target was dipping into the proton beam at ISIS, where the pions were created and then directed to the mice hole using several quadrupoles, dipoles, decay solenoid in such a manner that momentum could be selected in broad range between 120 and 260 MeV over C. Muon emittance could be selected at various values, and also high muon purity was obtained. So the details of that experimental campaign can be seen in various papers, which I quote here. Going to the next slide, the essential part of the experiment was obviously magnets. So the cooling channel used two types of magnets. The spectrometer solenoids, two of them, where the tracker, main mice detector tracker, was hosted in a uniform magnet, contained other coils which were used to match the beam to the other parts of the experiment, and the focus coil which was directly providing tight focusing on absorber, and also was constructed in such a way that the polarity could be flipped, which is the typical method to avoid buildup of canonical angular momentum. So the experiment was operated in two modes, the so-called solenoid mode, when the polarity was preserved between upstream and downstream spectrometer, and in the so-called flip mode, which is where the polarity is being flipped across the focus coil in the center where the absorber is located. We use three types of absorbers shown on the next slide: lithium hydride absorber, liquid hydrogen absorber, which also incorporated aluminum windows, and plastic wedge absorber, which is used for longitudinal emittance studies. The main tracker detector, which was in the uniform field of the spectrometer solenoid, was measuring positions in 5 stations of scintillating fibers. And by reconstructing a helix in the magnetic field, that allows to reconstruct the phase space of each individual muon on the reference plane. That's a general reconstruction method which is used in mice, and details how it is actually done is presented in several papers. Also, there were other detectors, in particular time of flight, Cherenkov, and calorimeters, which were complementary and actually very important, providing particle identification. And in particular, the combination of time of flight and momentum reconstruction in the tracker was very useful in down selecting the sample used in the analysis. So that also can be found in the papers mentioned here. So the mice was the first single particle emittance measurement which we performed, and so we were able to reconstruct emittance particle by particle. And for instance, we could present typical coupling existing in solenoids for the first time using this unique reconstruction, which is shown here in various components of the phase space in this plot here. So another very important quantity which was used in reconstruction is the single particle amplitude, which allows to build one-to-one correspondence between the particle distribution in the form of a phase space, where you can draw various ellipses with various size of emittance, into the histogram of amplitudes, because amplitude can be associated to a single particle, and the mean amplitude is then associated with RMS emittance. So this is the central quantity which we used in analysis of the flip mode data at 140 MeV/C, where you can see the histograms of amplitude in various cases in empty liquid hydrogen, where the absorber was evacuated, full liquid hydrogen, no absorber at all, and with lithium hydride absorber. So you can clearly see for the samples with different emittance, 4, 6, and 10 millimeter normalized emittance beams, you can clearly see that if you compare the distribution upstream and downstream, you clearly see that the distribution downstream is becoming more dense towards the lower amplitudes, which is a clear signal of cooling. And you can also see the correlation between the size of emittance. So you basically see stronger effect for higher emittance samples. Again, this can be even better seen if you compare ratios of cumulative distribution function, which basically tells you that cooling is present when this value is above 1. And you clearly see again the very good correlation between cases where you have full liquid hydrogen or lithium hydride present, where this value is above 1 for after you compare number out or number in. And this is in particular for the values of amplitude which are below the dashed vertical line, which is an indication of the acceptance of the channel. And below that value, it goes below because we have scraping, which is where there is a limitation of the acceptance. This result was also, in particular, this result was presented in Nature earlier this year, and we now also have this result presented in the solenoid mode, where we can also see heating if we reconstruct even lower emittance sample, but the cooling signal is very clear here. And this result was presented at this conference by Tom Lord during the poster session. Also, another way we also are able to see the cooling signal precisely using the RMS normalized emittance is the change of emittance downstream, upstream minus downstream, which is the delta emittance shown here in this plot for both liquid lithium hydrated liquid hydrogen, both using no absorber and also using empty channel. So the cooling signal with blue is where there are absorbers, and it's clearly below zero, which is a clear indication of cooling. This is done using the rejection sampling at the upstream tracker, which enables to down select a sample which is better matched to the tracker and also to the absorber. This result is presented here at ICHEP by Paul Georges in the poster session. MICE continues doing analysis, and we are also working on towards analysis with wedge absorber. Data analysis is work in progress, but here we hint some results from the Monte Carlo simulations where you can see a clear effect of a wedge absorber with reverse emittance exchange, where comparing no absorber on the left and wedge absorber on the right, you clearly see the decrease in longitudinal phase space in the middle right plot downstream, which basically means that somehow indicates that the longitudinal emittance is increasing, while you have a clear increase in 4D transverse phase space density, which basically means cooling in 4D. This will help to understand longitudinal cooling once this can be also established in data, and this is an essential ingredient for the muon collider. This is also presented here at ICHEP in another poster by Craig Brown. So here is my summary. Muon cooling is the last in principle challenge for neutrino factory or a muon collider. And MICE has measured the underlying physics processes that govern it. And in unprecedented single particle measurement, MICE has made the world's first observation of ionization cooling, which was published in Nature earlier today. And I believe strongly this opens the door for high energy muon accelerators as probe of fundamental physics in hopefully not a very far future. Thank you very much.
Thank you very much for this very interesting presentation, and congratulations again for the first observation of ionization cooling, Yaroslav. So
thank you very much.
Yes, any questions? Witold.
Witold Kazanecki, CEA Saclay. Could you give us a feeling for how much of a reduction, of an emittance reduction you observe? Because I don't see any numbers in the last two slides.
I think that, first of all, the observation which is published in Nature is basically qualitative, but you can have a quantitative observation here, right, in the slide 17. It's a change of emittance in millimeters over the initial emittance.
So if I take the right end of the plot, it's approximately, it's a little less than 10%. Is that correct?
That's correct. Yes. That actually the experiment was always designed to show somewhere between 5 and 10%. Actually, 10% was supposed to be in the final stage, which was not realized. So something like 5% is correct. Yes.
Thank you.
Any other questions? So what are the next plans of this collaboration?
MICE is decommissioned at the moment. Well, it has been decommissioned. So at the moment, we are continue doing further analysis. And for instance, we are hoping for the real another publication on the results, which is shown on slide 17, and also on the work on the wedge absorber, which is very important for longitudinal cooling. And we also will look into how these MICE results, which have been collected, can inform potential future designs of muon collider. I think that's a main direction of my collaboration at the moment. Obviously, the new muon collaboration is being formed. We had first meeting relatively in June, I believe, and people from my experiment many of them are very much interested in joining this activity.
Very good. I don't see any other questions, so thank you very much, Jaroslav, again.
Okay, so thank you very much, and I stop sharing now. Right?
We now go. Yes, please. So the next speaker is Daniel Schulte from CERN, who is going to talk about prospects on muon colliders. So Daniel, you have 15 minutes and there is 5 minutes for discussion. So Daniel, please.
So thank you very much. So we'll talk about the prospects of muon colliders on behalf of the forming international muon collider collaboration. So just for those that are not fully aware, muon colliders have been studied in the past, mainly in the US. That activity was stopped after the last P5 process. There was still some continued effort, especially in the K on mice, and some in Italy on an alternative scheme to produce muons. For this European strategy, a group of directors of different laboratories was asking a working group to actually provide input to the European strategy because there was no muon collider collaboration. And so that working group, chaired by Nadia, has actually then looked at the muon collider and recommended that a collaboration should be formed to investigate that because it looked promising. And the European strategy said that a muon collider should be part of the R&D roadmap. And then these directors from the laboratories established an international muon collider collaboration by July 2nd. Okay, the physics actually in the previous talk was already mentioned. It's basically, if we go to very high energies with lepton colliders, we get precision physics and discovery potential all together. And that, for example, allows to measure the a triple or a quadruple coupling of the Higgs. Now, if you look at the colliders that were actually proposed in Granada, so that had a CDR, that had a solid design at that moment, you can see them shown in the graph on the left. Here you see the luminosity and the energy, and you see that actually the highest energy point was click with 3 TeV, center of mass. And if you look at the cost of that project, 18 billion, all integrated, all the 3 stages to go up there, and the power consumption of about 600 megawatts, that is quite expensive and probably the limit of what we think can be afforded. I mean, some people might think it's less. It's roughly comparable to the FCCHH as a total project in this case. So what can one do to go beyond that? Well, from the US proposal, I mean, it wasn't a proposal from the studies, there were parameter sets up to 6 TeV, and you can see here actually the power, the luminosity divided by the beam power for those, comparing to a linear collider, click, and you see that in a linear collider, the luminosity per beam power stays same, constant with energy, which is one of the reasons why it's difficult to get to high energies where you need more luminosity. While in a muon collider, it can actually linearly increase. So that was quite interesting. The muon collider itself, there are 2 proposals. The proton-driven one, that one which has been developed in the US, consists of a proton complex where you provide a very dense proton beam, very intense proton beam. You send it to a target, you produce lots of pions, you capture the pions, let them decay. They decay into muons with a certain probability. You collect the muons, and then you send them into a complex where you cool them by ionization cooling. You combine bunches to further enhance the phase-space density, and then you cool more. This was discussed in the previous talk already. Then you X-ray to very high energies in a system of Linux and rings, because you have to be rapid because the muons don't have a long lifetime. And you collide in the collider ring with the highest fields. So this would allow you to actually maximize the number of collisions that the muons do perform before they actually decay. In the US study, there was no CDR and not a coherent baseline of the machine, no cost estimate, and they did not extend to 10 or more TeV. So there is quite some work left, but it looked promising. In terms of technology development, there were quite a number of ingredients. Mice was one of them, so you saw that. There were also measurements of cables. HTS cables are needed for high field magnets. You need a very high field solenoids. You need very high accelerating fields in a magnetic field, which is very difficult. Normally you would have breakdowns, so that has been demonstrated. And very fast ramping HTS magnets actually also have been demonstrated. So lots of bits and pieces were there. That's why we felt confident. What we proposed in Granada, so before the European strategy concluded, was a tentative timeline, which is technically limited. So it means this, if this is considered the highest priority, this is what could be done. Then it will be depend on resources. And you see this would have consisted of 4 years to arrive at the baseline design, both with the detector and the physics and also the machine, and also to design a test facility. So this would bring you to the state that you can decide on a test facility, on spending a significant amount of money on the study of this collider. Because then you would need 6 years or so to construct and exploit a test facility and optimize the design. So this would be already a relatively costly process. And that would allow you then to understand whether you can commit to such a collider. And then you would actually go into a technical design if you decided that this was the right thing. And then you could go into approval and so on. So this is technically limited. So the objective for the collaboration is that in time for the next European strategy update, the study will aim to establish whether the investment into a full CDR is can be justified and what a demonstrator would cost. So these are two elements that the European strategy needs to consider. And for that, we'll provide a baseline concept, well-supported performance expectations, look at the risks, the cost and the power consumption drivers, and identify the R&D that needs to be done and the demonstration that needs to be done. It will focus on high energies, 3 TeV and 10 plus TeV. 3 TeV because it's well above a Higgs factory. So if there's like a superconducting linear collider or FCCEE, you will be stuck at a few hundred MeV, maybe going up to 1 TeV with IOC. And then a 10 plus TeV because that should allow to understand the ultimate reach. And that would be well above also a normal conducting linear collider like CLIC. And I think it's not possible to do that at reasonable cost with CLIC. And then we will look into other synergies with neutrino Higgs factory and look at the R&D path and design the demonstrator. This has been defined from the European perspective because it was European driven. Now we will have to see how the other regions can be integrated, like there's this NOMAS process in the US now, and certainly interacting with them as much as possible to support that and maybe get the support from the US will be very important as a short-term goal. I should just say the next European strategy, probably documents have to be handed in 5 years down the road. We made a tentative target parameter set for each of the 3 different energies we are looking at, 3 TeV, 10 TeV, and then because it's 10 plus, also at 14 TeV, you see that the luminosities we achieve correspond to what the physics requires from us. And if you look at the beam powers, even the 14 TeV collider has 20 megawatts of beam power, which is quite reasonable. CLIC at that energy would need something like 130 to 200 megawatts of beam power. Okay, the source of the muons actually is the same for all of them. So it's just a high energy and that changes. I can not go into muon production and cooling very much. You heard quite something about that in the past talk. It is challenging. So the source, because you need a very ambitious proton beam. Your target is very challenging because you have a significant shock if your proton beam hits the target. One looked into liquid mercury, which came close to the performance. Actually, we were limited in the number of protons that you could send that into the jet. But then you might want actually a solid target, and there needs to be more work done on that. You also need this cooling scheme, which has high field solenoids, very high gradient normal conducting RF targets. Lots of power, so the radiation issues will need to be looked at. And currently, the paper design does not fully achieve the final emittance goal. It misses it by about a factor 2. So we need actually to review all of the designs. There were ways hinted how you could improve that, but that needs to be worked out. The high energy part mainly consists of two parts. There's the accelerator itself, which brings the beam to full energy. And then it's injected into the collider ring, which is optimized for minimum size. And so this uses the highest field superconducting static magnets, while the acceleration could consist of either an FFAG, where you inject the beam at one energy, and then you can actually tolerate a variation of the beam energy by a factor of 4 or so, in this case in one direction. Or it would be a fast ramping rapid cycling synchrotron. So it would ramp the magnet strength together with the beam energy up. And you would need to do that within a millisecond or so. So these two complexes are the cost drivers, and they are actually the limitation in the energy reach, because everything before them in our first order approach would remain the same. So one needs to look at that. I think it's very important also to realize that this accelerator ring is likely quite significantly larger than the collider ring, because these fast ramping magnets could be normal conducting, and then they would have a much lower field than the rings in the collider ring, the magnets in the collider ring. So just to show you some example challenges one needs to face for the rapid cycling synchrotron. So we ramp the magnets up. There is some scheme, I cannot go into detail here, where you mix superconducting and normal conducting magnets, which allows you to drive the normal conducting magnets against the superconducting ones initially, and then you go through 0 and add to the superconducting magnets, so you double the leverage of your fast ramping magnets. These pulsed magnets need to ramp in something of the order of milliseconds. It depends on the exact parameters. And that is a challenge. It defines the size of the ring. It's really 80–90% fast pulsing magnets. Normal conducting could work. HTS could be of interest. The ramp rates are in the moment like almost 2 orders of magnitude away from what we need, but this is something that should be developed in the future. It is important, the energy you need in these magnets is very high. So you have lots of stored energy in the magnets, which you then have to efficiently recover after each cycle. Because if you don't do that, it's at 14 TeV, 200 megajoules. You do that 5 times a second. So you lose 2 gigajoules per second. That's 2 gigawatts. So that doesn't fly. So systems to recover the magnetic energy exist, but this is at a very large scale and it needs to be very efficient. So that needs to be developed. And existing systems need to be pushed and improved. And for an FFAG, it's a very challenging lattice, and the magnets are also a challenge. Another thing that's important, the RF needs also to be quite efficient, and it needs to face the issue that the bunch charge in the muon collider is very high. And then between bunches, because it's just one bunch circulating, there is quite some time before before it arrives again. The charge is actually 10 times the Halloumi bunch charge. So that requires quite some thinking, because you want lots of stored energy to make the single bunch effect easy, but then that means low frequency, but then with a short bunch that you need also in the collider, you get into a higher order modes. So this system will be quite interesting to optimize and design. In the collider ring, you need very high field dipoles because you want to minimize the ring size. You also have losses because all of the muons die. When they die, they produce 2 neutrinos and 1 electron or positron, depending on the charge, mostly. And these electrons and positrons will be somewhere lost in the ring. And that corresponds at 14 TeV to 400 watts per meter. It's actually independent of the energy. It depends just on the magnetic field. So the aperture of the magnets needs to be shielded with some substantial tungsten shielding or so. Or we need to have open midplane magnets where these decay products can actually escape from the magnets. And we need very efficient cooling because you need to have these losses at high temperatures to avoid that the cooling power that you need is very huge. We also need combined function magnets because we cannot have straight sections. We cannot afford to have quadrupoles, normal quadrupoles. There need to be some combined function magnet instead. And then at the interaction point, we need very strong focusing. And there, at higher energies, actually the beta function is decreasing at the IP. So that makes that the focusing system becomes more and more challenging as you go to higher energies, because the beam size, the initial beam size, the divergence around the IP, so the size when you start here, does not shrink towards higher energies as it normally would. And you need to bend a tougher beam, much higher energy beam. So that needs to be worked out. And we need to have an efficient design for that. And then in addition, you need to have very short bunches. It's 1 millimeter at 14 TeV in a large ring. So you need to find ways to make sure that the beam is longitudinally frozen very much. So that is quite some interesting optics design and beam dynamics. The MDI, there will be a presentation after here, just to say that these decaying muons also decay close to the interaction point, and it's at 14 TeV about 40,000 per meter and bunch crossing. At 3 TeV, it's actually more because it's the same power per meter. So just because the lifetime is shorter at the low energy. And so you need to shield your beamline and the detector, and you see a plot here, and you will get more information about the simulation in the next talk. At lower energies where we have simulations, this might be fine, but at higher energies, this needs to be studied and a design needs to be made, actually, because the results may depend on details of the beamline design close to the IP. And that will make a challenging detector development with effective masking, high granularity, fast timing, and clever algorithms. There are some side considerations, because certainly when this was born, we were thinking about a project in Europe. It could be somewhere else. And so there's a question, could we reuse the LHC tunnel? There's actually a proposal to use the LHC tunnel for a 14 TeV accelerator and a combined accelerator collider ring. So the combined accelerator and collider ring was a proposal from Vladimir and David. And you could imagine that the collider ring could be smaller, about half that size, 14 kilometers. And so you could imagine still having the accelerator in the LHC tunnel. The other option is that for the 3 TeV, you could put the accelerator into the LHC tunnel. The collider ring itself, the optimized size would be just 4.5 kilometers or so. And if you make the ring larger, you would need more current, because you have a longer path before you hit the next, before the bunches collide again. So there we would just use the LHC potentially as for the acceleration. The limit on doing this comes actually from the neutrino radiation. So the two neutrinos that the muons decay into, they go through the Earth. They have a very small interaction probability with the Earth, but once in a while they can actually scatter and produce hadronic showers. And if they do that just before they leave the surface of the Earth, they can actually lead to some radiation. And this radiation obviously needs to be as small as possible, because people don't like that. I mean, we talk about radiation that's similar to or below even the natural level, but still you don't want to increase that in a significant way. So if you look at that, there are some mitigation methods for this. For example, this will be most critical where you have long straights, where you have maybe injection and also the detectors. But this would point to 2 locations, one in each direction. And so there you could imagine that you buy these locations, or you put them into a place where there's no problem. Then you can try to vary the orbit of the beam by several sigma, and that would already help, because this opening cone is very, very small. So by bending the beam, you would move this up and down, and therefore spread the radiation, reduce it. And you can do some more gymnastics in the straights to avoid that they're fully straight. They are a bit more like a wiggler or so, or helical undulating. And certainly you try to minimize the beam current for a given luminosity. Now, based on some first order estimates, simplified estimates, and some gut feeling, one would see that having a 3 TeV accelerator in the LHC tunnel might well be possible. There need to be still some work done, while it is less clear that the 14 TeV accelerator or even the combined accelerator and collider could be put into the LHC tunnel. That needs to be looked into. A new tunnel would always be better, because it would be designed to not have so many straights as the LHC, which created a problem, and which happen to locate, to point to locations right now, because nobody thought about this. An alternative scheme is being developed for the source, which could potentially need only a smaller muon current. That's this dilemma scheme, where you send a positron beam into a target, and it at 45 GeV, and then the positron can actually produce muon pairs together with the electrons from the target, and those have a small emittance, and then they be captured in a ring. So you have a small ring here which captures subsequent shots of the muons, and then after some time, after about a lifetime of the muons accumulated, then you eject the beam and accelerate to high energies. this is very challenging technically. The target would be very challenging to get the positron current you need is very challenging. It's a rate of 10 to the 17 or so positrons per second. And currently, this scheme does not reach the luminosity goal. So work is done to improve it, and it could be an interesting option for high energies if that can be made to work. So
could you please try to wrap up?
Yeah, the path
Thank
forward.
You very much.
What we need to do is we need now to form the collaboration. So all the partners, many of them are new, need to take ownership. We have a web page where we will start to put information, and we have mailing lists to which you can sign up. And the work will start now this fall, and some meetings already, like for the detector, already took place. So this is a way how you can subscribe, and so we'll be informed about this activity. And there are a number of people that I have to thank and a number of collaborations. So thank you.
Thank you very much for a very interesting and inspirational talk. So questions for Daniel? I don't see any hands raised. I have a question. Is there any, can you identify a few examples of synergies in R&D between these neon colliders and say FCC technologies development?
Yes, I think in terms of the magnet technology, the muon collider needs similar magnets than the hadron collider. So the design is somewhat different because of this radiation, the additional complication. But it's very much the same effort to develop the strongest superconducting magnets that are possible. In terms of RF, it's superconducting RF, so that is synergetic at some level with the FCC-EE and also probably with the superconducting linear collider, because it's high field superconducting RF. So yeah, there are a number of synergies. There's also maybe some synergies, for example, on the lattice side. I have the feeling that the collider ring lattice has some similarities in problems, not in all the details, with what people do at light sources now, where they try to, I mean, there's some effort to try to get steady state microbunching in light sources to produce, and there you need to control the longitude and the phase space of the beam very well. And that's what you need to do in the collider ring.
Okay.
Just as an example, but we don't know the detail. It just feels like this must be synergetic. Sorry.
Okay. Thank you very much. I see Yaroslav has his hand raised.
Yeah, can you say about the requirements for the beta star?
Yes, it was in the table. So the beta function at 14 TeV should be 1 millimeter. It is, so the way this works is the assumption is that you have a longitudinal emittance which hopefully is preserved during acceleration. So that's one of the things that we need to carefully ensure that this is indeed the case. And then you have an energy acceptance in the big ring. So you try to make the bunch in the big ring as short as possible, and you achieve, with this emittance, you could reach 1 millimeter. And then you try to profit from that, making the beta function also 1 millimeter short. And then as you go to lower energies, it would be increasing proportionally, I mean, as 1 over the energy. So that's why it becomes more challenging towards higher energies. Does that answer your question?
Yes, but it seems to be order of magnitude more challenging than in, for instance, high Lumi LHC.
Yes, exactly. No, this is absolutely challenging. The aperture of the triplet, Rogelio Thomas had a quick look into that, and I mean, we talk about several tens of centimeters, and a triplet which is also a few dozen meters long. So no, this is not a simple thing. That's why this was on the slide. This is one of the things that will limit ultimate. I mean, this could be one of the limitations in our energy reach in the end. So that's why we need to work out these parts in addition to the source. This needs to be really understood. What is the limit? What can be achieved in the future? Our technology.
Thank you.
Okay, I think we should stop here. Thank you very much, Daniel, again.
Thanks.
And
we
move on. Thank you. Yeah. To the next talk by Francesco Colamati from INFN Rome, who is going to talk about a flexible tool for beam-induced background simulations at a muon collider. Francesco, you have 15 minutes and 5 minutes for discussion. Thank you.
Okay, thank you very much. Do you see my slides correctly?
Yes.
Perfect, thank you. So, good afternoon, everybody. I am Francesco Collamati from INFN Rome, and I will talk about a flexible tool for beam-induced background simulation at a muon collider. Please let me start by thanking all my colleagues that are listed here that work in this topic in the field, let's say, of the newborn international muon collider collaboration. I would like to start by focusing the problem, and because as we said in the previous talks, we can think about the muon collider as some sort of the dream machine for the future of high energy physics. I'm not going through all the reasons about this that we just discussed, but just let me quote two of them. First advantage is that all the energy is available in the interaction. Again, I won't bore you again with this plot for the third time in a row, but you see that it is very interesting and to have this possibility of going to high energies. And regarding the machine side, the much reduced synchrotron radiation losses means that these high energies are almost easily, let's say easily, achievable within reasonable amount of spaces. So for all these reasons, such a machine can give us a huge amount of interesting physics. But as we all know, everything comes at a cost. And actually, in this case, I would say at a few costs. Again, I'm not going through all of them, but I wanted just to list some of them to focus the problem. First of all, it was already said now, we have to produce these muons. And we all know that besides the so-called, I would call it traditional approach that uses protons to produce these muons, a more recent proposal has been done of using positrons to directly produce these muons. I'm not going into detail. This is not the topic of my talk, but I just want to stress that all the study I'm presenting today does apply to both situations with some differences, but the principle is the same. Then once produced, these muons will have to be handled, and in particular, we have to consider the muon cooling that as was nicely just explained, is a problem in particular in the proton-driven scheme of the production of muons. But the problem that I want to focus our attention today here is the ones related to muon decays. In fact, if we keep as the final goal of this study the huge amount of interesting physics that we can reach, we have to deal with the fact that these muons will decay all along the machine. And this will lead to several issues. I'm just putting a couple of them. For example, these colliding beams will obviously lose intensity, and this can be a problem, but we can think about addressing this problem by, for example, thinking a continuous top-up of the branches from a muon source. But the other problem that we should focus, the other question that we should try to answer is, what about decay products? In fact, we are dealing with high energy muons. We are talking about 10, 14 TeV muon colliders. That means that we will have a vast amount, a plethora, I would say, of secondary and tertiary particles with such a variety of energies. So these particles will have lots of effects that we can summarize in these three categories. For example, we have to be very careful and avoid magnet quenching, obviously. Then there is all the issue, I would say, the chapter regarding radiation protection that Daniel just highlighted. But what I wanted to focus your attention on today is the fact that it impacts detector backgrounds, because I think that this is the aspect that leads us directly to the central question in this topic. Okay, muon collider can give us a huge amount of interesting physics, but are we will be able to see this physics at the very end? Because it is clear that this is the final question. So the beam-induced background that we call BIB in the detector can, for the reason we saw, severely impair its performances. That's the reason why the MAP collaboration studied the problem in detail. In particular, they implemented 200 meters around AP in the simulation with a careful reconstruction of the geometry. They focused their attention on the 1.5 TeV center of mass energy configuration. Then what they did was to use this Marx code to simulate and transport secondary and tertiary particles from the muon decays up to the detector. And the result is what you see, for example, here on the right. This process ended up in the design and optimization of these two tungsten nozzles that are depicted in yellow here in the bottom picture that are made again of tungsten and ended up to play a crucial role in the background mitigation inside the detector. Now, I don't go in detail on the results of the study by map, but just to frame the problem and to understand what we are dealing with, I want to show you this plot in which we have the number of particles per bunch crossing as a function of the distance from the muon decay to the AP. Here, each color corresponds to different particles, and we see that the bulk of these particles, they are photons, neutrons, and so on, come, let's say, from the last 25 meters from the IP. As far as the energies are concerned, just a quick look to know what we are dealing with. The electromagnetic component is low energy, is about the MeV energy. Neutrons and charged hadrons have about half a GeV, while muons easily go up to tens of GeV. And it is obvious because we are dealing with high energy primary muon beams. So this was the MAP study. What we did in the recent past was to, in some sense, complete this study, performing for the first time a full event reconstruction. I'm not showing details of the study because there is a dedicated talk that is going on right now in a parallel session by Massimo Casarza that is showing updated results for this study. So I suggest I refer you to its slides that you can find on the Indico page or on the reference here of a paper we recently published. What I want to tell you here is that this study demonstrates that challenging physics measurements are possible. So let me spend 30 seconds to recap what I told you up to now in order to be sure of framing correctly the issue. We saw that the muon collider has outstanding physics capabilities, but this beam-induced background that arises from muon decays can indeed impair detector performances. That's the reason why a first study in a particular case, the 1.5 TeV case, has been done in the MAP program, and the results in this case suggest that challenging physics measurements are possible. So one could argue here, okay, let's move to another problem. We have lots of problems with muon collider, this has solved one. Okay, we don't think this is the case. We don't think this is the take-home message from this arrow, from this slide, because we instead think that this is telling us that the beam-induced background must be kept strictly under control. And this has to be done, the test has to be possible in each machine configuration. In fact, let me highlight that this study took several years of study and optimization by the MAP colleagues and was just for 1.5 TeV center of mass energy. I mean, just for one of the possible configuration of such a machine. Instead, today, we want to be able to, for example, to change the beam energy. We are talking about high energy muon colliders, so 10 and more TeV. That means changing the machine optics, or also we want to be able, for example, to apply other optimization of the MID, for example, regarding the nozzles or something like that. That's the reason why we felt the need for a flexible tool to go from the machine optics to the Monte Carlo simulation. So this is the context of the study. The quest for the tool identification started from the assertion that FLUCA is, as everybody knows, one of the most common general purpose Monte Carlo software. In particular, is used for radio protection studies. Moreover, it does natively support very complicated and detailed geometries in a plethora of different settings, as I'm showing here in this picture. However, the problem is that the manual construction of such geometries is difficult, time-consuming, but moreover, I would say it's mostly not scalable and flexible. That means that at the end of the day, it's error-prone, and it's something that we want to avoid. That's the reason why we decided to couple this FLUCA, this Monte Carlo code, with this program that is named FLUCA Line Builder. That is a program that has been developed by Alessio Mereghetti at CERN in the recent past, that is exactly aimed at automatically build accelerator geometries And is composed by two parts. The first part is the so-called Fluka element database that, as the name suggests, is nothing more than a collection of some models of single accelerator devices. For example, here you see a prototype of a LHC dipole. And this database is coupled with a line builder, that is the program itself. Let's say it's a Python program that reads the machine optics file and populates the simulation, inserting at each position the needed magnetic element. The result of Fluka line builder is what you see here in the picture, in which you can understand that you have the full reconstruction of the machine with such a high detail and precision in geometry that once you have such a geometry, you can think of simulating whatever you want inside Fluka with its accuracy, well-known accuracy. So this is the identification of the tool. Let's move to the procedure to show you how we used it. First of all, we decided as a first goal to reproduce the map results at the 1.5 TeV center of mass energy. This is obviously in some sense less interesting because it is the only case that has already been studied, but we thought it was honest and intelligent to start from something for which we had a benchmark. So the idea is that we benchmark our study on this configuration and then we move to other configurations. So we took from our map colleagues the machine optics for this configuration. We had to play a little with it because of some differences in the format and so on, but we did manage to use it in line builder. Then we built a first Fluka element database implementing some, I would say, first order magnetic elements geometries. For example, here in the picture, you see the first approach to a bending dipole. But what I want to stress here is that this can be an iterative job in which time after time we can add details and precision to the representation of these magnetic elements, and they will be transferred easily, automatically inside the final simulation. For the time now on, we have implemented dipoles, quadruples, and sextuples. And also the detector, as you see here in this picture, in which the detector is obviously the gray envelope, while the brown stuff inside are the famous nozzles. And we added it to the geometry too. I want to highlight here that this import of the detector is performed in an automatic way by means of a script that reads directly the GDML file of the detector. And I think it is a very important point because in this whole study, the name of the game is to have some flexible tool. That means that if in the future, but I don't know how far future, we will be wanting to change the detector, for example, changing the number of layers or its shape, we want to be able to transfer this modification down to the full simulation easily and without any pain. And this is performed by means of this GDML parsing. So at the end of this work, this is what we produced by means of Fluka line builder. And you see from the top view, we built the whole muon collider. Actually, we just built half since we don't need the whole machine, to be honest. And so we are talking about more than 1 kilometer of collider. And this is the experimental cover before the insertion of the detector. As you see, you can recognize this funny trajectory of the bending dipoles. And these are just some plots that confirm the closing orbits of the machine. While the picture on the right is a 3D representation of the interaction area itself, in which you have the beam coming from the beam pipe in light brown from the rear, and then there is the nozzle and the detector. So this was regarding the geometry. Let's go to the results. I want to highlight that the results I'm showing you are very, very preliminary, since the build-up of the geometry was a time-consuming task. So we just started to play really with the simulation. And we started, as I anticipated before, by reproducing the 1.5 TeV case. So we are firing 750 GeV plus. And I can show you as first results the flux of produced particles. And I don't know if you read it correctly. From top left, we have electrons, photons, protons, pions, muons, and neutrons. And these are the fluxes of these particles. The beam direction is the one indicated by the arrow. And I think this is very interesting. I mean, we didn't digest totally these results because they're very, very fresh. But what I want to show here is what we can obtain from this study in a total automatic and flexible again way. So I think this is very interesting to compare relative weights of such contributions. This was before the insertion of the detector. Then we inserted the detector, and now I can show you in my last slide also the flux of particles that enters the detector. And this is most interesting because for the first time, we see in action the effectiveness of the nozzle, the famous nozzle, because the green line is the case in which there is no nozzle inside the detector, and purple line, as a comparison, is the case in which we have a nozzle. So if we focus on the rightmost plot, that is the energy spectrum of electrons entering the detector, we understand the huge impact the insertion of this nozzle has, because we are talking about a four orders of magnitude reduction of the low energy electron flux. That seems interesting enough, not paid, let's say, in terms of other secondary particles if you look at the other plots. On the bottom left plot, we have the color plot, let's say, of the neutron flux of neutrons entering the detector, while on the bottom right, we have just a picture of the beam pipe entering in the nozzle, hiding the detector to see how it happens in the inside. So let me conclude by summarizing what I showed you. I'm showing you that the beam-induced background in a muon collider experimental area is mainly due to muon decays and can indeed impair physics measurements. That's the reason why we develop a powerful and flexible tool for simulating such sections, starting from the optics, coming up down to the Monte Carlo simulations. So we identified the Fluke line builder as the tool, and we started to use it, setting up the geometry and the detector. Next steps from here will be, well, first of all, as I anticipated, after the validation at 1.5 TeV, we want to go further, for example, starting to study the 3 TeV and center of mass energy machine, that is a different machine. Then we plan to submit a SNOMAS letter of intent, but the real take-home message I hope I deliver with this talk is that we think and we actually hope that this can be the beginning of a prosperous and I would say fun work of a Monte Carlo-driven MDI optimization of such a machine. And it's obvious, that this work cannot start without involving some, let's say, accelerator physicists, MDI experts, and so on, and everybody that want to join us in this study. Thank you for your attention.
Thank you very much, Francesco, for an interesting talk. Any questions, please? I don't see any. I have a quick question. Do you have any plans to benchmark?
I missed you. Sorry.
Okay.
Sorry, I lost the connection. Okay,
yes.
Back again. Do you have any plan?
To benchmark the tool you developed specifically against an experimental setup.
That's interesting. Yeah, something. I mean, against some experimental data, new data.
Yes, yes.
This is a nice question. I mean, I don't see it so easy in the near future because here we are using it to simulate the whole muon collider. Obviously, it can be used, and I have to say that the line builder itself is already in use for LHC, iLumi LHC study, so it's nothing new. I mean, it was used for other topics.
Of course. Yes.
So I don't know if we will be able to find some sort of benchmark also for this study, but now we are thinking a little bit more, let's say, bigger, I would say, to the whole machine for the moment.
Right. Okay. Thank you.
Thank you.
Any other comments? If not, thank you very much, Francesco, again. And we now go to the next talk by Matthew Jones from Purdue University, And Matthew is going to talk about resonant extraction and extinction measurements for the mu2e experiment.
All right,
Again,
thank you for the
15
introduction.
minutes plus 5, please.
All right. I hope you can hear me and you're seeing my slides.
Yes, perfect.
Yeah, so this will be primarily focusing on the beam delivery system for the mu-D experiment. The mu-D experiment is going to be a search for charged lepton flavor violation. It's under construction at Fermilab. Here is at least some of the collaboration sitting in the new, or standing in the new experimental hall that's been built for this experiment. Although this will focus on the beam delivery systems, it's worth mentioning the motivation for doing this experiment. There's no symmetry principle that prevents charged lepton flavor violation, and we certainly know that because of neutrino mixing, it's allowed in the standard model, and we can calculate the rate at which a muon would turn into an electron. And it is about, well, it's too small to be measured by any of the experiments we could conceive of. But there's also no reason why this would be why this type of conservation would be protected in any other scenarios of physics beyond the standard model. And so it's a very natural process to look for, because if we observe anything, then it's a clear sign of physics beyond the standard model. And obviously people have asked the question, is it a symmetry of nature? Is it conserved for quite some time, dating back to Pontecorvo? And so here's the evolution of the limits that have been placed on the processes like muon decaying directly to an electron and a photon, coupling to a virtual photon in the electric field of a nucleus, where a muon will decay to an electron. And then there's sort of the internal conversion of the photon process to produce 3 charged electrons. And so the limits that have been placed on these processes have evolved over the years. The best limit is by the MEG experiment. And so the goals of the COMET experiment in Japan and the mu-D experiment at Fermilab is to improve on these by about 4 orders of magnitude. The experiment itself is shown here. A proton beam is used to make pions. The pions decay to muons, and the muons are transported down a solenoid. They're stopped on an aluminum target in this case, and then they're allowed to decay. They'll either be captured by the nucleus, or they'll decay in orbit, or if they decay in the charged lepton flavor violating mode, they can produce an electron with a characteristic energy that will be intersected by this carefully constructed tracking detector. The electrons from normal decay and flight of muons will pass through the hole in the center of the detector and not leave any signal. So this is the construction of the experiment. Not shown are the cosmic ray veto system, which is potentially an important background. The stopping target monitor, which is sort of like a luminosity monitor for measuring how many muons are stopped on the target. And then I'll say more about the extinction monitor throughout the talk. The sensitivity of the experiment is calculated by figuring out how many muons we can reasonably produce. That's determined by the number of protons on target. And so the baseline is about 3.6 times 10 to the 20 over about 3 years of operation. The process that we're looking for is this essentially monoenergetic 105 MeV conversion electron. And this will sit just beyond the endpoint of this very long but very small tail from the regular decay in orbit background from the muons. And the width of this peak is determined by the momentum resolution in the tracker. One of the key background processes for these types of experiments is radiative pion capture. And with the design of the experiment, this can be kept low enough that it won't be an issue. But that motivates the critical design requirements for the way the beam is delivered to the experiment. And so most of what I'll be describing is the beam delivery systems that will allow us to control any background processes that are in time with the beam on target. So the pulse beam structure that's used for this experiment is motivated by reducing radiated pion capture. That happens when pions that are produced at the same time as the muons are transported to the stopping target. And a pion that's stopped on one of the target foils can emit a photon, that photon can then pair produce and produce electrons with a range of energies, but they could potentially lie in the search window for the signal we're looking for. The way we avoid this being an important source of background in the experiment is to produce the particles, mostly muons, but potentially also pions. These are then transported to the stopping target down the transport solenoid. The pions, however, will decay with their characteristic lifetime, which is much shorter than the lifetime of the muons. And so if we blind the experiment for of order, say 10 pion lifetimes, there will be no more pions present in the data sample and will only be sensitive to muon decays. So that motivates the pulse beam structure. We look for the muon decays in this live window, and then we repeat the whole process to increase statistics. Now this works provided we don't have any protons arriving at the production target out of time with the main beam pulses. Because if we produce particles at the production target during this live window, they may also produce pions. And the pions can undergo this radiative pion capture at a time when we don't expect it. And so the critical parameter for this experiment is what's called beam extinction. And that's the ratio of the number of out-of-time particles between the proton pulses to the number of in-time particles in the beam pulses. And this needs to be controlled and measured at a level of about 10 to the minus 10 between the proton pulses to achieve the limits we're interested in. The time structure is actually very well, on aluminum at least, is very well suited to the accelerators that are available at Fermilab left over from the Tevatron era. The beam will be delivered by producing batches of 8 GeV protons. These will circulate in the recycler ring. These will be grouped into bunches that are then transferred to the delivery ring, which is this triangular ring, which used to be part of the anti-proton system for the Tevatron. The natural period of circulation in the delivery ring is 1.7 microseconds, which is well matched to the requirements of the experiment. But the natural extinction of the circulating beam is only about 10 to the minus 5, just from the bunch structure and the timing of the period around this ring. Nevertheless, this is the beam that has to be extracted and delivered to the experiment. And it has to be gradually removed so that we deliver a large number of very low intensity pulses to the experiment to control the occupancy in the tracker. And so the beam delivery system consists of a resonant extraction system that will gradually peel off the beam that's circulating in the delivery ring with this 1.7 microsecond period. The goal is to remove a small number of them on each orbit and deliver them to the experiment, maintaining the required extinction. The way this is done is using this resonant extraction system. The two conditions that are needed for this resonant extraction are operating the tune at close to a third integer resonance, but also the presence of a strong sextupole field. And when these two conditions are met, the phase space for the beam will be divided into these two regions. A stable region of phase space where the beam will circulate around the ring is in sort of the center of this region. And then another region of phase space develops where beam will migrate away from the central orbit in this unstable region. And the boundary between the stable and the unstable regions of phase space is called the separatrix. And that's created by this combination of this operating near the resonance and the strong sextupole fields. So in this way, we can gradually force the beam onto the unstable orbit, and then it will have large amplitude oscillations and then be extracted gradually at each turn. Beam which is on this unstable orbit will have large amplitudes, and they can be then removed from the orbiting beam by a series of electrostatic septa. This is the scheme shown here. There will be 2 electrostatic septa, and beam that is in this high field region will be deflected. It will go through a quadrupole, which is part of the regular lattice of the synchrotron. It can then go through another electrostatic septa where it will be deflected a large enough distance that it can then go through a kicker magnet and be deflected vertically, whereas the central orbiting beam will just pass straight through all of these systems. So that's how we can extract beam gradually, but the extinction is only about at the level of 10 to the minus 5 at this point. And we require an additional factor of at least 10 to the minus 5 to satisfy the requirements of the experiment. And so to achieve this, there is a system of magnets that's going to be installed. And these will deflect any out-of-time beam into a system of collimators. Now, we would like the beam that's in time with the main pulse to pass straight through this system. And so the magnets actually will have to be pulsed at this frequency or this period of 1.7 microseconds. Now, pulsing a magnet at this, this frequency is not technically possible. And so instead, we excite it with an AC field, an AC current to create what we refer to as a resonant AC dipole system. So on this graph here, it shows the amplitude of the exciting current in the magnet. There's actually a superposition of a low frequency and a high frequency component. And that means that as the in-time beam passes through this magnet, it's essentially in a field-free region where it's relatively flat in the amplitude of the field. Outside this region, the amplitude is significant, and that will create the deflection of the beam and send any out-of-time beam into the collimator. So the experiment will be designed with two of these systems. There will be two identical 3-meter systems, each of which is constructed out of 3 of these 1-meter AC dipole units. And so these have been prototyped, and we're procuring the parts for the final system. The result is that there's this transmission window, which has very high efficiency for in-time beam, but then any beam that's out of time will be deflected into the collimators. And so the beam that's coming from the delivery ring is shown in this green curve with the 10 to the minus 5 extinction. That gets multiplied by the transmission function for the AC dipole, which is very high efficiency for in-time beam, but then will deflect any out-of-time beam into the collimators. And so the product is this, the transmission function for the beam delivered to the experiment, which does achieve this, the required extinction of less than 10 to the minus 10. So that's how we are going to achieve this level of extinction required for the experiment. Now, it's also going to be very critical both for the commissioning of the delivery system, but also for the experiment itself to be able to measure the level of extinction that we achieve. And to do this, we've constructed a dedicated system for measuring the extinction. The relevant extinction for the experiment is not the beam delivered to, not the beam extracted, but rather the beam that's actually impinging on the production target. And so the system that we have is looking at particles scattered and produced at the production target through a system of collimators. There's a bending dipole magnet so that there's no direct line of sight, but then a small fraction of the phase space of the particles produced at the production target will make their way to this extinction monitor system. The extinction monitor system will just be counting particles that move from that emerge from the system of collimators. And it's constructed out of pixel sensors that were repurposed from the LHC experiments. In this case, it's Atlas IBL sensors with FEI4 readout chips. And there are a total of 8 pixel planes. And using this, we can measure very precisely, we can detect and count the number of particles that we see emerging from these collimators. These have been constructed. We were hoping to have operated them in test beams at Fermilab this summer, but that has been delayed. But the point is that with this system, we can very accurately count the number of particles. This doesn't require a complicated reconstruction technique because it's primarily a pattern recognition problem where we look for hits on 4 or 8 pixel planes that essentially line up in the pattern that you would expect for tracks. We expect there to be about 40 tracks through the system for in-time tracks for the nominal pulse intensity. But we have to be able to be fully efficient for any particle that emerges from the collimator that's out of time, because that would represent non-extinct beam. So if we count anything that's out of time, that's the numerator in our extinction calculation. we have to count the large number of particles very accurately for the intensity of the pulses that are in time. That is our denominator, and we just add those up, and over the course of several hours, we get to this level of 10 to the 10, and can set a limit of less than 10 to the minus 10 on the extinction. We can also use the intensity of the pulses that are measured using the extinction monitor system, as well as using a wall current monitor that will gradually average the intensity, the measured intensity of the pulses that are extracted. These are used to regulate the rate at which beam is pushed out of the stable orbit into the extraction orbit in the delivery ring. And so both the extinction monitor and this wall current monitor that are used in this feedback system to control the intensity of the pulses that are delivered to the experiment, to try to equalize them. So the status is that we've built all the extinction monitor hardware. It's at Fermilab. It was intended to be operated in a test beam, and I will be able to show results. That will have to wait until next year. The electrostatic septum that's needed for the delivery ring is progressing. It's being tested. And the current construction schedule has the accelerator and the beam line commissioning to be in 2021. That will allow us to commission the extinction system, the beam delivery, and the feedback systems before the final experimental solenoids are installed in 2022. And then the final project will then be delivered to physics operations in 2023. So that's the summary. To be able to do these kinds of experiments, or these next generation charged lepton flavor violation experiments, critically requires performance of the accelerator. We believe the beam delivery system that's been designed and is being constructed is challenging, but it's achievable for the requirements of this experiment. And most of the components that are needed are on track for the schedule that I just showed. And we hope to be able to show results from test beams to demonstrate that we'll be able to meet these requirements, hopefully next year. So thank you.
Thank you very much. Questions, comments for this talk, please? I do not see anything. I have a question. I was wondering if you could give us just a sense of about Mu2E2 and what the extinction challenges for that might be.
So that's undergoing some discussion right now at Snowmass.
Okay.
I think one of the critical things for the next generation or Mu2E2 type experiments would be a different beam structure entirely. So the 1.7 microsecond system is ideally suited for capture on aluminum, but other nuclei like gold would have different time structures. And so one of the critical aspects of the Mu2E2 type experiments is going to be producing the high quality extinction with a very different beam structure. And so that's one of the big. I think the system that we've designed for measuring the extinction in this case would be equally applicable to any of the next generation Mu2E2 type beam delivery systems. It really works very well to repurpose LHC technology, and there's a huge new generation of pixel devices being developed for that. And so I think the same principle would work extremely well.
Very good. Thank you very much, Matthew. Okay. Thank you. Let's proceed to the next talk then, which is by Marco Romagnoni from INFN, University of Milan, and he will talk about future perspective for bent crystals in accelerators. Again, 15+5, Marco.
Hello, thank you. I will now proceed to give you to share the screen. That's the moment. Okay. So thank you to everyone. I will now proceed to talk about future perspective for band crystal in Accelerator. Doesn't slide? Okay, sorry. Okay, so in crystals, atoms are arranged in a very ordered manner, in a very specific position at a nanos and in a nanometric structure. And these structures, under a center point of view, they can be present planes or rows or of aligned atoms. So particles incoming along this direction will have a very different phenomena inside the matter with respect to amorphous material, as much as a different path is taken while walking in a wild jungle or walking into a garden. So when particles enter the crystals while being aligned with the lattice plane, they observe a continuous potential, which means that they can be trapped inside a potential well, this potential well, if their incoming angle is low enough. Of course, positively charged particles will be bounded between the two adjacent planes of atoms, and negatively charged particles will proceed along on this plane of atoms. Of course, scattering will be much different. With the positive particles will have a much reduced inelastic collision with nuclei, of course, and negatively charged particles will have much increased inelastic collision with nuclei. This means that positive particles, once channeled inside the crystal, can travel a long way without having any strong scattering event. This means that bent crystals can act very efficiently as a waveguide to this positive particles beam. And because channeled particles will follow the curvature of the bent crystals. And the steering power achievable with such a method, with this technology, is much larger than artificial magnetic dipoles achievable at the state of art. As you can see in the table, we have a comparison with some crystals and the equivalent magnetic dipoles. You can see which is in the order of the hundreds of Tesla, or two applications that I will soon explain in more details. The evolution of this idea was first theorized in 1976 by Siganov, and was soon also observed in experiment with very low efficiency, but still was detected. And afterwards, there was a constant activities to increase increase the efficiency of this technology, as you can see in the plot on the right. And this increase, very strong increase of efficiency, is given by better simulation to achieve an optimal bending and length of the crystal. So a design of the crystal theoretically which was increased, and as well as a technological advancement in the bending, shaping of the crystals, as well as the preservation of a perfect lattice quality during such processes. In the laboratory of Ferrara in the last decades, there has been very intense activities in production and experiment of bent crystals, collaboration, international collaboration, such as UNI at CERN, and CRISPIN and Seldon ERC project. We have a large clean room facility to produce these samples, as well as facility to characterize the bending state of this specimen that we produce, such as a laser interferometer, which can scan the optical surface of our samples with nanometric resolution, as well as an high resolution diffractometer, where we use a monochromatic X-ray beam to directly observe the bending of the lattice planes of our specimen. Of course, with this, there is also an intense activities of test beam to actually test the steering efficiency of the produced crystals at several different facilities, such as the extracted beamline of CERN SPS, the MAM Accelerator at the University of Maine, and in the United States, SLAC as well. So for application, the first application that I will discuss is the collimation of a beam in an accelerator. Of course, collimation is a critical feature in order to have an intense beam. Often the efficiency of the collimation system define the maximum luminosity allowed inside an accelerator for radio protection motivation. Usually it is performed by using a collimator, which is a block which is about 1 meter of length for LEC, for examples, which scatter the beam, the particles near the beam trajectories onto the dedicated absorber far from the beam. And this is very difficult to do at tera-electron volts scale, because particles are very energetic. They scatter very little, and it's very difficult to dissipate all their energy. So a bent crystal is a very interesting solution that was proposed in order to take the particles which travels beside the beam trajectory and to deflect them in an orderly manner, so not a stochastic process like the amorphous collimator, but deflect them via channeling into an absorber. This will result in a reduction of secondary particle produced along the beam line, the beam trajectory, and a more precise control of the particles, of the deflected particles. This is very important also for ion beam collimation, because ion beams tend to produce a shower of other particles. Upgrade, following this concept, there is also the possibility to have a beam extraction. In fact, the stirred particles, positive stirred particles, conserve most of their energy and conserve a small angular divergence. So they could be exploited for other experiments. If they are directed, for example, instead of in an absorber into an external beamline. This is, for example, an external beamline for LEC will be a unique tool for experiment or new experiment. And or we could deflect the beam halo into other specific area inside the accelerator for a dedicated experiment. The last possible application that I will discuss is spin precession. In fact, via spin precession, we can study electric and magnetic dipole moment of particles. In particular, electric dipole moment is strongly suppressed in standard model, so any observation will lead to a clear signal of new physics. And magnetic dipole moments of baryon will allow a precise study of QCD calculation. Of course, for fast decaying particles, this is impossible to be done with a magnetic dipole. Thus, a bent crystal, which hundreds of Tesla equivalent steering power, will be the only way to explore, to investigate this dipole moment, electromagnetic dipole moment for particles such as charm baryon. And this is proposed in the seldom experiment, which use both extraction and spin precession application. At LHC, a first crystal will deflect the protons from the halo of the beam into a target before LECB. And in this target, lambda C charm baryon will be produced and collected into a second crystal, which will deflect them into the LECB detector. And during this deflection, they will give, they will allow to have the spin precession of these particles before their decay. And thus, in LECD, then retrostructure of the original spin state of the lambda C particle after being channeled by the crystal will be performed. A test beam was performed at HA in Billnight of SPS in the north area of CERN with a 2/3 proton beam and 1/3 pion, positive pion beam of 180 GeV energy. The particles are tracked before, trajectory is tracked before the crystal and after the crystal in order to identify the angular kick given by the crystal deflector. Two crystal were studies, and this is the efficiency deflection plot for the two crystals. Of course, these are still preliminary data. But we can see that there is still a good agreement between experimental and simulation. And we can see that the germanium works very well at such high bending and will be probably one of the first candidates for a seldom experiment. And now, so up until now, we talked about planar effect. But when we are aligned to the planes of atoms, but when we are aligned to the rows of the atom, so when we are aligned to the axis of the crystals, we can have other types of effect. In this case, for example, for bent crystals, the particle scattering will be always converge within a critical angle, incoming angle, will converge along the axis direction. This means that there is this mechanism of stochastic deflection, which is very efficient both for positive and negatively charged particles, which was not possible for negative charged particle in case of planar channeling. Moreover, we have particles undergoing very strong electric fields while crossing the crystals in axial alignments, which for ultra-relativistic particles allow to overcome linear QED condition. And so it's a unique possibility to study this kind of non-linear events. In this case, resulting in the radiation loss of most of the particle momentum. This was tested at the H4 extracted beamline of SPS at CERN with a 120 GeV electron beam and positron beam crossing a bent crystal, germanium crystal in axial alignment. The deflection, the particles were tracked before and after the crystal in order to measure the deflection. And afterwards, the charged particles are deflected away from the crystals and leaving the photons produced inside of the crystals to be measured inside a gamma calorimeter. Here we have the results for deflection. We can see that the electrons, since they cross the crystal much closer to the nuclei, they undergo large scattering and they have a much larger divergence, but still they are mostly deflected into by 100 microradians, while for positron we have a much more precise deflection to 100 microradian, which is the curvature of the bending of the crystals. And we see the energy loss that for the electrons, they lose almost all their energy within a large 200 microradians angle with respect to the crystal axis. And on the other hand, positrons, while they are aligned with the axis, they lose much less energy, and only for misaligned crystal misaligned trajectory, there is a strong energy loss comparable to electron case. So in conclusion, we can see that we have a large steering power achievable with band crystals, and there has been a large R&D for LSC collimation, and also novel solution for experiments such as beam extraction and fast decaying particle studies of ADM and MDM. And also axial effects widen the possibility to negatively charged particles and offer a unique opportunity to study QED in nonlinear cases, and as well as give a collimation possibility for positron and electronic beam for collimation, which is coupled with both deflection and energy loss of the collimated particles. And with this, I thank you very much for your attention.
Thank you very much, Marco, and thank you for sticking close to your time limit. So any comments or questions for Marco? I do not see any. Well, thank you very much again.
Thank you.
And I suggest we move now to the last talk of the session,
Sorry,
which is...
I will stop share.
Yes, please. Thank you. Which is given by Benedetto Di Ruzza from Trento Institute. And the title of the talk is Proton and X-ray Radiation of Silicon Devices at the TIFPA INFN facilities in Trento, Italy. So 15+5, please.
Okay, thank you very much. Can you see my slide, right? Yes.
Yes,
okay.
we can.
Okay, okay. Thank you. And hi, everybody, and thanks to everybody for wait up to now for this talk. And I'm Benedetto Di Ruzza. I'm working in the TIFPA, that is a section of the Italian National Institute for Nuclear Physics that is located in Trento. In this talk, I will show how it's possible essentially to perform some silicon detector studies also in a medical facility. I will describe, first of all, the Trento Proton Therapy Center, that is the oncological center located here in Trento, and some key element of this center, the key element for the physics point of view, that are the cyclotron and the experimental area where we realize some tests for different type of sensor. And I will show you some tests we started at the end of last year, and that we hopefully will resume soon in September when all the operation with the medical facility will restart. So the Trento Proton Therapy Center is one of the 3 centers in Italy where it's possible to treat oncological patient with protons. This center is started the clinical activity in 2014 and is equipped with 2 different gantry for patient treatment. And since the beginning was also equipped with a experimental area where it's possible to perform biological experiment on cell, but also on the physics device and innovative device.
The K of this center, the source of the proton, is a cyclotron that is a commercial one, that is essential, that is realized by EBA Corporation, and is a cyclotron that works at fixed proton energy, 2030 MeV. That is the typical energy used for medical application, but is able also to, the energy can be degraded up to 60 using the opposite degrader system. 62 MeV up to 230 MeV is the official range energy that is used for all kind of oncological application for protons. As I said, the center is equipped also with a experimental room that is a place completely devoted to experiments, both biological, biophysics, but also physics. And essentially in this room, we use the beam when is not required for the patient. It means in the late evening, starting from 7 p.m. or generally in the Sunday. This type of activity was closed in the last months due to the COVID pandemic, and we will resume this activity hopefully in September. The center, the oncological center, remained open all the time and worked all the time, even in the last month. Now I will show you some tests that we started and some plan, some other work that we already planned to do for in the future. Essentially, we want to use the beam to perform radiation damage bulk damage on generic silicon sensor. First of all, on SIPM or small sensor. And I will show you some consideration and some tests that we already made. Essentially, the beam is in the experimental area spread with a Gaussian profile, and the sigma of this Gaussian is changing with the energy, but is very well measured. This spread, this sigma, during the commissioning of the beam, and in reference one there is a detailed description of all the beam. So even if also the number of protons that are delivered in the experimental room change, not only even when the extraction current is constant. And this happens because of the delivery system. But also this quantity is very well measured. And so we started with a condition of 100 MeV protons. And in this condition, the beam is a well-defined number of protons, is delivering a very well-defined number of protons per second, because the beam is almost continuous. And we consider a irradiation time of 20 minutes. That is a compromise for this type of cyclotron. Cyclotron. Because for medical application, the accelerator cannot work all the time, night and day, as in high energy physics.
So is required some stop, and we found that 20 minutes is a good agreement in order to keep safe all the things. Doing performing this irradiation, we have a sigma of the beam that is 5.68 millimeter in the isocenter point of the experimental area. And with this number of all these elements, we can do an evaluation on the number of proton that is eating a detailed circle of radius r. So we have in 20 minutes, we have all the beam that is delivered, that is spread with a Gaussian profile, and doing an evaluation of the fraction of the beam that is eating a small area inside this Gaussian. For example, if we consider a circle of 2.5 millimeter, we have the 9% of all the beam, means all the proton, delivered proton that is eating the area that is in this picture is depicted in red. Or considering a circle of 3 millimeter, the fraction increase up to 13%. So in this way, even if the beam is not uniform, we can evaluate the average fluence of that is eating a circle inside the beam. I used this value at 3.5 and 2.5 millimeter and 3 because these are the typical dimension of a small silicon sensor like SIPM or chip prototype. In page 10 here, there is a summary of all the conditions for circular area with the radius from 1 millimeter up to 4 millimeter. And in the last column on the right, there is the average fluence on that is eating this circle after 20 minutes of irradiation. We see that we are starting to this number of particles on centimeter square is can start to be interesting for performing bulk damage studies on silicon detector. If we consider silicon detectors for medical or space application, which does not require very high fluence. So summarizing this part, this setup can be used for small sensor irradiation. For example, SIPM and small chip prototype of small prototype of pixel detector, for example. And considering that the energy that the equivalent radiation damage of 100 MeV proton is equivalent to 1 MeV neutron equivalent, this setup we see that is useful for study of bulk damage for space medical application. We already made this test in 2019 on FBK SIPM, and we had some interesting results. And we resume soon is the measurement hopefully in September. Let's consider now what we can do if we need a more uniformity beam or if we want to test if we want to perform a test, irradiation test on large area detectors. Since 2018, the biological, one of the two lines of the experimental room was equipped with a device called the dual ring, and this is able to spread using with scattering, not magnetic effect. Essentially, the beam in a radius of 5 centimeters and 10 centimeters. And in this circle is possible to have a very uniform beam, even if the intensity is lower than the one. This device was designed in order to perform experiment on biological cell flasks. But now the plan is to use the same device also for silicon sensor irradiation. This device works at the 148 MeV fixed energy. And here there is, in this slide, there is a schematic overview of the device and a picture of the present status of the device. In the reference 2, there is a detailed description of this device. And in October, we will use for the first time this device also for performing irradiation tests on a board that have to be used for space application. Let's go ahead. There's another way to where it's possible to perform a test in a biological facility on silicon sensor, and is using X-ray, because X-ray are required for the surface damage studies. And here in Trento, in the TIFPA, we have also a X-ray tube that is already used for biological studies, and is set up to 195 kV. This is not a good voltage for silicon surface studies, but this voltage can be set up to 40 kV. That is the correct one. I started to do some tests with this machine again using SIPM, FBK SIPM, and test structure SIPM. And the results are interesting. The only point that have to still be fixed in the future is the dose measurement, because the dose measurement system that is used for biological application, in our case, is a calibrated farmer chamber, is not enough for for silicon irradiation devices, because this one is calibrated only for emission spectrum at high voltage, and the low voltage emission X-ray is out of the range of this chamber. So for the future, we are planning to acquire a dose measuration system realized by a diode, and in this way also the X-ray irradiation can be performed with this machine. So conclusion, I showed the preliminary study and that we are doing here in the TIFPA Trento in order to perform silicon irradiation studies, both for bulk damage and surface damage, using the beam that is used for medical application and the X-ray machine that is also used for biological application. And we hope to resume soon all this kind of study and give you more information. Thank you for the attention, and take a look also at the following slides where there are a lot of useful reference and other information. Thank you so much. That's all.
And thank you very much, Benedetto, for this very important talk. The talk is open for questions or comments. I do not see any. So I'd like to thank you again for your talk. And this brings us to the end of this block and for this session. So I'd like to thank all the speakers first for excellent talks and for staying mostly on time. I'd like to thank the organizers for the interesting program, as well as the attendees. And I wish you a good evening. Bye-bye, everyone.
Thank you. Bye-bye.
Thank you, everybody. Bye-bye.
Thank you.
Goodbye.
Thank you. Bye.
Bye. Thank you.